Radiotherapy with protons. Radiotherapy uses the fact that radiation is dangerous for biological tissue. If a cell gets too much dose, it will die. This is what we use in normal radiotherapy with electromagnetic radiation. You irradiate a tumor and eliminate the dangerous cells. Now, the difficulty in radiotherapy is not so much to damage the tumor. That's easy. You just irradiate long enough and the tumor will get a dose and it will die. The difficulty is much more to spare the surrounding healthy tissue, the tissue that is in the flight path. And here, particles, and in particular protons, have an advantage over the conventional radiotherapy with electromagnetic radiation. And this is the reason why we do radiotherapy with protons. The price to pay you see on this picture here, this is a conventional LINAC to produce therapeutic gamma or electromagnetic rays. And this is a typical proton facility. You see it's much bigger, very heavy, and this means it's more expensive. And why do we do this? The answer, of course, is in the physics. You have here on this axis the penetration depth of the radiation into the tissue. You have here the dose, which is the effect of the radiation. And the protons have a defined range. They stop at a certain depth. And this is where they create the biggest damage. And if you have a tumor that has an extension in proton range, by changing the proton energy, you can cover the whole target volume with this blue sum curve and get a good coverage of the target. And photons have a completely different behavior. They have most of the effect close to the surface. In the region of the tumor, it's about the same, but what you have to compare are these surfaces. What is the dose outside the tumor? This is the dose that you do not want in case of photons, and in case of protons, it's not zero, but it's much less. And this is the reason why we use protons for radiotherapy. What are the main components of such a treatment facility? You need an accelerator. In many cases, it's a cyclotron, like in this example here. You need beam lines that direct the beam with magnets into certain treatment rooms. And from the treatment rooms, we have two types. This one, which we call fixed beam line, the protons coming out here, you can hardly see the vacuum tube passing through some components that shape the dose. And then the patient seated, for example, on a chair, could also be lying on a patient table, but the beam line is always fixed. And in contrast, you have these machines, which we call gantry. A gantry is a beam line that can rotate around the patient, and this allows us to come with the proton beams from different incident angles. And so in the crossing point of these various beams, you get an enhancement of the dose. This is what we use. This is the cyclotron that we use. It's a commercial one, not built by us. It was built by this company called Accel, which later was bought by Varian. So Accel built the first prototype of this superconducting cyclotron, rather compact, rather service-friendly. And PSI has the first one, the prototype. And this then, when Varian took over this company, this then became the cyclotron that is installed in all the Varian ProBeam systems. And we use it since almost 20 years now, and it's really very reliable. Yeah, you have an inside. You see a person here. So for an accelerator, for cyclotron, it's quite compact. 1000 nanoampere is the maximum current that we can get, and that's more than enough for our therapeutic applications. It must not be a cyclotron. It's also possible to do particle therapy with synchrotrons. This is a facility in the north of Italy next to Milan, which is sort of a spin-off from CERN. The people that have built this facility, they were at CERN before. But you see already the big difference is that you need more space for a synchrotron. And if you think about clinical facilities, space in a hospital is always an issue. So this is why mostly cyclotrons are preferred for proton therapy. This is how the facility at PSI looks today. So we have in one corner the cyclotron that I talked about. We have the different beam lines. And we have 1, 2, 3, 4 treatment rooms. These 3 treatment rooms have been built by us. And they were in several aspects pioneering facilities. And I will talk in more detail about that. And this gantry here is a commercial gantry. It's exactly a variant pro-beam gantry that we integrated into our facility. And I want to mention one point here. The cyclotron, as you know, gives a fixed energy, but for the clinical application, you need a range of energy. And so you must reduce the energy from the 250 to whatever you need. We go down to 70 MeV clinically. And for this purpose, here in this region, we have a degrader. It's a system of carbon wedges that we can drive into the beamline, and then the protons travel through more or less material. They lose more or less energy, and so we can reduce the energy. And remember this degrader because it will become important towards the end of my talk. But there is also a similar proton therapy just the other side of the road here in Chulalongkorn Hospital. And I had the opportunity earlier this year to visit this facility. So this is exactly the same gantry like the one that we have installed at PSI. Let's talk about how do we shape the dose to give the form of the tumor. We have 2 different possibilities to do it. The classical method works like this. You take the proton beam from the accelerator, let it pass through a scattering foil which broadens the beam. You bring into the beamline a collimator, a piece of metal, for example, that has the form of the tumor cut out, and then you position the patient downstream of this collimator. This collimator has the individual form of the tumor, so it has to be individually produced for each patient. But once you have such a collimator and once you have positioned the patient correctly, it's a relatively simple technique because the only quantity you need to control is the dose. You switch the beam on and switch it off in the right moment. So this is why with this technique proton therapy started in the 1960s, early 60s. They were all using this technology. PSI started in 1984 as one of the first places in Europe to use protons. And we concentrated on one special indication, the treatment of melanoma in the eye. So you see here the view into the pupil of one of our patients, the background of the eye, and here is a tumor that grows into the eye. These tumors are dangerous. They destroy the eye. But worse is they easily build metastasis in other organs of the body. So if you don't treat such a tumor, the patient risks to get, for example, liver metastasis, and that can be fatal for the patient. So when you discover such a tumor, you have to remove it. And before protons, removing the tumor means you have to remove the eye. Now, most people have 2 eyes, but if you can keep both eyes, it's a big advantage for the patient. And this is why this indication was sort of a pioneer field for proton therapy, because you have really a big advantage for the patient. We collaborate with ophthalmologists who prepare the patients in an operation. You see the ophthalmologist there, and here this is a model of an eye. It's not a real eye. Under anesthesia, the ophthalmologist pulls the eye a little bit out of the socket and shines with a lamp through the eyeball. And maybe you have seen on the first slide, these tumors are melanoma, so this is skin cancer in the eye, which means these tumors are dark. So they cast a shadow. You can see very clearly where exactly is the tumor. And then the position of this tumor is marked by stitching very small metal clips onto the eye. We use tantalum, which is a good biocompatible metal, and they are very small. And then the eye is put back into the socket. And it sounds very dramatic, but our eyes can move very well, so the patients can tolerate it quite well, but it's invasive. A couple of days later, the patient comes to PSI. We prepare face masks, which adapt to the form of the skull. The patient has a bite block in the mouth, so you really cannot move the head anymore. And then this mask is fixed to the treatment chair, so the patient is fixed. And then we rotate the patient in the direction of the beam line here. And this is what you see in the next picture, the beam coming from here. Here in this position is the collimator. And we do not yet switch on the proton beam, but we take X-rays. And on this X-rays, you cannot see the tumor. It's transparent for X-rays. But you see these metal clips from this surgery. And you compare here in color, this is the nominal position, and you see the shadow where these clips actually are. So in this photo, the patient is a few millimeters too low. The chair is connected to an hexapod industry robot, so we can correct the position, lift the patient, take another X-ray until the position is fine. And then we do the irradiation. In the case of these eye tumors, we have only 4 sessions, 4 fractions, where we give quite a lot of dose in one fraction, 16 gray, so that we reach a bit more than 60 gray after 4 sessions. It's quite a lot of dose from the point of view of radiobiology, but the result is extremely good. We have treated now, I should update this number, but by now it's more than 9,000 patients. And the success rate is really good. 98% cure, meaning here 5-year local tumor control. This is the quantity, so it's really working very well. No danger of metastasis, tumors not growing anymore. And also important, in most cases, we can conserve the vision of the patient. The patients can see as well as before the treatment. So for this kind of tumors, protons have become a standard. So it's really a very, very successful therapy. Motivated by this success, PSI in the late 1980s decided to expand the proton therapy program to also treat other kind of tumors, not only these eye tumors, and use a completely different irradiation technique, which we at that time called spot scanning. Nowadays it's more called pencil beam scanning. And here is how this works. We take again the proton beam from the accelerator, but we leave it focused and use the fact that the magnet can change the direction of the proton beam. So we set the proton beam, we set the magnet for a certain value, and then switch on the beam, set one dose point, switch off the beam, change the magnetic field. You see, we scan one line in the target volume. And now something here happens. We bring material into the beamline and then repeat the scanning. And this material means that the protons lose a little bit of energy, which means they don't reach that far in the patient. And we get a second line, but a bit more proximal. And now it's clear how this continues. You can change the energy again, adapt the range of the scanning field. So with this technique, it's possible to cover 3-dimensional volumes inside the patient without the need for patient-specific hardware. You don't need collimators here. But it's more complicated. You need to control the dose, but you also need to control the position and check the position. So the idea to do this is already quite old, but you had to wait until the 1980s when the technology was there. You need fast power supplies for the magnets. You need fast control of the beam. You need fast analysis of the beam profile to check the position. And all this is applied particle physics. It became available in the 80s. And the team that had the idea to build this at PSI, they were particle physicists, but they knew how to do this. And they teamed up with biologists and medical doctors and decided to build such a machine. And the result is this one, our Gantry 1, which is, as far as I know, the first implementation of this pencil beam scanning worldwide. So the you have here a schema of the beamline. Everything that is green can rotate, and what you see in the photo is just this part here, this part. There is one, the beam comes from here, gets directed out of the beamline, then parallel to the original axis. We have the scanning magnet here, and then a 19-degree magnet, which is under this big cover, that bends the beam towards the patient. We have the nozzle. We have the okay, yeah. The nozzle where we have this range shifter that I explained. It's a system of 40 plates of 5 millimeter polyethylene plastic that we can move pneumatically into the beamline. We have detectors, the dose monitors, and also position sensitive detectors. This is here the nozzle, and the beam comes out of this slit. Gantry 1 can do the scanning in only one dimension. We found that this is already complicated enough for the first machine, so we do the second dimension by moving the patient table. And the patient started in 1996, and for 12 years, this was the only spot scanning gantry worldwide. GSI in Germany, they also started a particle therapy program with protons and heavy ions. And they also use a scanning which is a little bit different from our scanning. We switch the beam off between the spots, whereas they do raster scanning, which means they do one spot and then very quickly move the beam without switching it off. So it's a slightly different technique. And this is why I can say for 12 years we were the only pencil beam scanning gantry. But they were also pioneers just a little bit later than we. So here's a statistic of the installed gantries. In blue, gantries that use the scattering technique, and in red, gantries that use the scanning technique. So there was a system here which had, I think, 3 gantries for scattering. This is Loma Linda in California, near Los Angeles. 96, our gantry 1, and for 12 years alone. And around this time, commercial machines became available. If you have the money, you can buy such a machine. You don't need a physics institute to develop it. And you see from that point on, really, the scanning gantries took over. And here you see nowadays, this is 2018, but the trend continued. Nowadays, a new center, most of them want this scanning technology. So what we started 25 years ago has become the standard, and we're a little bit proud about it. So after a couple of years with Gantry 1, we thought, what would we improve from the experience that we gained with the first machine? And we constructed the second gantry, which you see here in this animation. On the patient table is just a phantom, a measurement device, but this is where we position the patient. And it has a lot of improvements. Some have to do with the clinical workflow, with the access to the patient during the treatment. In Gantry 1, depending on the treatment angle, sometimes the patient was 2 or 3 meters above the ground. And this made us always a little bit uncomfortable. If there is some problem, you have to reach to the patient and you first have to climb up there. So Gantry 2 is designed in a way that you always can easily access the patient. But more interestingly, we also improved a lot on the scanning technique. Especially, we put a lot of effort in making the scanning faster. And fast is important not only to reduce the treatment time, which is typically a couple of minutes, depend on the volume of the tumor, but a couple of minutes. But scanning speed is important if you want to treat moving targets. A tumor in the brain is always fixed, but if you have a tumor in the pelvis and the patient breathes, it can move a few centimeters. And this is a problem for spot scanning, because then you don't have this precision, which is the advantage of protons. But if you are fast enough, you can there are ways to compensate for this organ motion. Some impressions how such a gantry is constructed. It's really heavy mechanical engineering, because you need to carry these heavy magnets, and you want high precision. You don't want that the whole thing bends, so it has to be massive steel. This is the 90-degree magnet of Gantry 2, the biggest one. Here it is mounted, here's assembled. You see the vacuum chamber and the black thing. This is a measurement device, a CCD camera to check beam profiles and beam positions. Then we make the room look a little bit nicer for our patient. And in 2013, we treated the first patient on gantry 2. One focus of the of proton therapy is the treatment of small children, because in a child it is even more important than in an adult that you only hit the tumor and do not damage the surrounding tissue of the growing organism. And the complication with children is that they have to keep quiet during the treatment, and and they don't like it. Adults sometimes also don't like it, but you can explain them. But children not. The smallest child that we treated was 8 months, so really they cannot understand it. So you have to treat them in anesthesia. It's a sedation, it's not really anesthesia. They still breathe spontaneously, that's the big difference. But still, it's an additional complication in the whole logistics. So we work together with the Children's Hospital in Zurich. They sent us a mobile anesthesia team to PSI. They start the anesthesia in the presence of the parents. Once the child is asleep, it's positioned on the treatment bed, then brought into the treatment room. This child here is lying on the back, has the head fixed by a bite block in the mouth. The bite block is fixed to the table. And the critical thing for the anesthesiologist is that they cannot be next to their patient during the treatment. They have to be outside of the treatment room. So they have to rely on their anesthesia monitors that send the vital signs outside, and they are just outside of the treatment room and watch what's going on. Very unusual situation, but we now treated almost 1,000 child patients like this, and luckily no accident, and the doctors now, they are also confident with this technique. After the treatment, the child is brought into a recovery room where it then wakes up, and then the parents can be present. Some words on the technology of the scanning. This is what was our goal for gantry 2. So we have this discrete spot scanning that I described in this animation earlier in my talk, where you go spot by spot, like in an old TV picture, compose the three-dimensional volume. But what gantry 2 can do is what we call line scanning. You move along the tumor, but you do not stop. You continuously move along the contour of the tumor. And this is a gain in speed. And there is something in addition to that what we can do. We have, from the gantry control system, we have access to the center of the cyclotron. In the center of the cyclotron, this here is the ion source. The protons come out here. They start doing their turn in the cyclotron. And here we have what we call the deflector plate. There we can apply high voltage, 1 kilovolt. And if you apply high positive voltage here, the protons are stopped because they see the positive voltage, they don't continue. Now, high voltage is something you can regulate very quickly. So this is a way where you can change the intensity of the proton beam quickly. There's a direct link from the scanning system on the gantry to the power supply of this deflector plate in the cyclotron. And this feedback loop allows us to very quickly change the intensity. So while we do the scanning, this here's an example where we just move the beam along one line. And we change this deflector plate voltage, and we see that the intensity vanishes. And here we do certain discrete steps. So this is a way where we have even one more degree of freedom that we can vary during the treatment. And this is all quite tricky and quite challenging from the point of view of electronics and controls, but it's interesting. So if you want to see more about PSI, during the pandemic, I did a video because we could not welcome visitors at PSI. So if you search in YouTube for PSI proton therapy, you will find a video where I give a tour of our facility and also a tour in the Synchrotron bunker, which normally you cannot visit with guests. You can check that out. Now let me come to the last part of my talk. And I expect many of you have heard this word flash already. This is a new, I think it started 2018, so already some years, but still a very hot topic in radiotherapy, not only protons. The meaning is the following. Normally radiobiology says what is important for the effect of a treatment is the dose. How much protons, how much photons do you give? But FLASH says it's not only the dose that counts, it's also how fast you apply it. If you do it very, very fast, like a factor of 1,000 faster, with higher intensity faster, you get a better sparing of the healthy tissue. So this effect that protons have built in is even enhanced. And there was a group in Paris, they started this here. You have always the reference in the slides. And I believe the slides will be available to you after this presentation, so you can check out these references. This is just an example with cells with electrons. You have the control sample not irradiated. You have a sample irradiated with normal dose rate, and the dark color means there is damage in the cells. And then you have the same dose, but with a higher dose rate, much higher dose rate, and it looks almost like the not irradiated sample. So that's interesting. Why is this? CHUV is a hospital in Switzerland. Some people from the Paris group moved to CHUV, and they continued doing these experiments with electron beams. And also here you have on the upper part irradiation with electrons, a certain dose, normal rate, flash rate. With the normal rate you see these black spots, and this is necrosis. This is something you do not want. It's an unwanted side effect in radiotherapy. So here you do damage to the cells, but here not. So interesting. They even treated quite early, this group in Lausanne, a human patient with a flash electron treatment, and you see the result after 5 months is really good. Now the big question is this also true for protons? These were all electron elements. And there's a lot of interest, was immediately a lot of interest from the commercial vendors of proton therapy facilities, because if you can treat with flash dose rates, you can treat patients more quickly, means you can treat more patients in one day, means you can make more money. So there's a lot of interest. And, and all the important vendors, they started experiments at IBA here and Varian, even now the clinical trials. And this here is a result from Dresden, which is an IBA facility. Let's not go too much into detail. If there is a flash effect with protons, you should see a difference between these two curves, or a difference between these two curves, and you don't see a difference. So question mark is no flash effect for protons, so the answer is more experiments required. This was published in 2019. End of 2018, Gantry 1, our management had decided this machine is old, it's still working very well, but we would need to upgrade especially all the electronics, because it was 25 years old electronics, no spare parts available anymore. So for clinical operation, this was quite a risk. It was decided that we should shut down Gantry 1 and do the clinical program with the 2 other gantries, which would be enough. So Gantry 1 was sitting there, and everything switched off. And then our boss heard about the flash, and then he came and said, can we do flash with Gantry 1? We said, yeah, let's take a look. Now, I'm coming back to this picture with the degrader. So the degrader is there to reduce the energy. And when you do that, the beam gets spread out, and you lose a lot of protons. They go left and right with the wrong energy. So when you go to very low energies, you have a very bad transmission of the beam line. When you go to high energies, you can get almost 100% through. So No, I forgot, do I have this graph? No, I have to explain it here. So in order to, and this means you get quite a range in intensity in the treatment room. And this is something which you do not like, because you have detectors that work well in a certain range, the dose monitors, but if you have a factor 1,000 variation in the intensity, you don't like that. So what we do is, we operate the cyclotron at a certain intensity. For the high energies, where we get a good beam transmission, we on purpose defocus these magnets here, so we get an artificially bad transmission. And then for the low energies, we focus them and we ramp the cyclotron up to the maximum current it can give. And then even with the bad transmission, we get more or less the same intensity in the treatment room. Now we said, what if we open the degrader completely and ramp the cyclotron up and we focus the quadrupoles? Then we should be able to get the full intensity of the cyclotron into the treatment room. And we did some first experiments in late 2019. See here, this was November 2019. And the important number, this is a measurement from profile monitors on the gantry, already very close to the patient table. The cyclotron current was very low, 0.2 nanoampere. And you see what we measure here. It's almost 0.2 nanoampere, which means 100% beam transmission. And our cyclotron can go up to about 1,000, or I say 800 nanoampere in stable operation. And if we go from 0.2 to 800, we get into the flash regime. So technically possible. Then we did, in January 2020, we did the first experiment where we put a scintillator block here. The protons come from here. We have a Faraday cup to cross-check the dose measurement. And actually, we measured dose rates of up to 9,000 gray per second. So yes, we are really in the flash regime. We were very happy. But this was January 2020. Then COVID came, everything stopped, sort of. Oh, did I skip one slide? Yeah, this one. So later in the year, in 2020 and then in 21, we were able to do the experiments that we wanted to do with the flash experiments. We took zebrafish eggs and irradiate them the same dose, once with flash, once not with flash, and try to see if there is a difference. So this is gantry 1. You see now it looks like a laboratory. And we are really very lucky, because most facilities that do flash experiments, they can do this in the night, and they have to change some things to do flash, but in the morning they have to put everything back because the patients are coming and everything must be perfect again. We have here a full playground for physicists. We can do everything we want. We can do all the changes. If we are tired, we go home. We don't need to clean up. It's really fantastic. Here are the these are Marie-Catherine Vosnin from Lausanne. She's leading the team of radiobiology there. So she provided the zebrafish eggs, and we prepared such frames. And you see we have here these Eppendorf tubes where we put a few eggs. And this is then mounted on the former patient table of gantry 1. And you see in this frame we have 20 samples. And the table is motorized because we used it to move the patients. So we prepare a whole frame and then close the area. And then we can treat very quickly 20 samples within 2 minutes with varying the dose rate, varying the dose, whatever we want. In Lausanne, where they have the electron flash experiments, they have to position one sample with the laser, then go out, close the door, one sample, go back, take the next one, align again. So it takes a lot of time, and we can do this very quickly. So it's really very good because we benefit from the existing infrastructure in gantry 1. Yeah, and this is then our control room where we do the treatments, and after we take the frames out and then do the analysis. I have to go a little bit faster now. And we have results from these experiments, but they're not so easy to understand. And I see, for me, it's a discovery. It's really, this is biology. And there are many, many factors, and it's much more complicated than physics. I like physics more. I can understand better. These are these embryos after a couple of days, I think, growing. And if the embryo is straight, it's a good sign. If it is curved, it's a bad sign. And you have here the control sample, so it's straight. You have a treatment with photons. And you see this is here deformed. You have a treatment with electrons. This is conventional dose rate, and this is flash dose rate. And yeah, is there a difference? Hard to say. And here, protons from our measurement, is there a difference? Well, maybe this is a little bit more curved than this one, but it's very difficult to say something. So the biologists, you see again the reference there, it's published. They do the analysis quantitatively. Let's just focus on this picture here. You have the control sample, so no effect. You have the photons, you get a strong damage. When you look at the electrons here, you have to compare this red column with these two others. It's a little bit better with flash. And protons, this is conventional, and this is flash, almost no difference. What does this mean? So we said we need to do experiments with real animals. So we started a session with mice. We positioned them. This is the left picture is Lausanne. This is the electron accelerator, and this here is PSI with protons. We have a copper block with a small hole inside as a collimator, and then just place we irradiate the brain of the mouse to see for neurological damage. And I have to skip this because this is how we validate if the mouse has shows neurological damage. So photos from these experiments, the mice are anesthetized so that they don't run away. We position them and then do the treatment. So the neurocognitive response, how much brain damage you create with these treatments, control sample, photons, quite a lot of damage, flash electrons, quite good. So there seems to be a clear effect. And then the proton sample, yeah, there is a little effect. This star means it's 1 sigma, but we want more than 1 sigma for a real clear effect. So we were asking ourselves, a mouse brain is small. Maybe we do not always hit the mouse brain. Maybe we shoot on the side and then we don't really get an effect. So what can we do to check if we really irradiate the brain? And the answer is we need a PET CT for the mouse to check after the treatment if the brain has been irradiated. And luckily in PSI somebody had a PET CT that can be used for laboratory animals. So we invited them to join us. So this is the PET CT. It's a commercial device. You can move it around the computer with the analysis, and here is the PET CT where you first, immediately after the irradiation, you take a PET image, and from the proton treatment, the irradiated part get a little bit activated. You measure this activation, and then the mouse is continued to make a normal CT. And because you know the geometry, then you can reference the activated image with the skeleton, and you know where the brain is. And this is one of the animals here in the PET CT. And this is a result. And if you look at the top line here, this was the first series of experiments that we did. And if you see here and here, we irradiate quite a lot the shoulders and not really the brain itself. So we improved the positioning of the mice. Improving the positioning means we taped their head with Scotch tape on the collimator. And then did the same, and you see it's much better. Huh? We we really put the dose on the brain. So I think this is fantastic. This is physicists and electronics and software engineers working together to make this scanning device. Then you have the biologists that come in with all these cell experiments and their expertise on radiobiology, and then you get this imaging in order to make these experiments really work correctly. So this is really very nice way to work together with different disciplines. This series has not yet been published, so I cannot talk about the results. But this concludes my presentation here on proton therapy. So you see here, this is part of our team, and this is just what I described. Different people from different backgrounds, different ways of thinking, working together because we have a common goal. We want the best benefit for our patients, and this is really very big satisfaction. Thank you very much.
Thank you, Martin. So yesterday we listened about electron and what we're going to use electron for, like a synchrotron light or free electron laser. And today we hear from Martin as the beginning of the day how we're going to use proton. Thank you very much, Martin. And we have some time, right? Maybe for some questions. Okay, please.
Thank you very much for the very nice talk. Like that covers an entire journey of developing tools, and that was like a really fun ride. So for proton therapy, when you show the calibration curve, that looks really awesome, but also really scary because like the penetration would also depend on the electrodynamic responses of the each part of the body too, right? I guess this is not very relevant when you talk about the eyes, but when you talk about other parts of the body that can have varying dielectric constant, how much does the effective range of the proton change when you use it to kill tumors?
You mean this curve?
Yes.
Okay. Well, the range of the protons change according to what kind of tissue is transversed, if it's bones or muscles, or it's different. And this is part of the treatment planning. We make a sort of a three-dimensional model of our patient based on CT information. Okay, of course, I talk all the time that photons are different from protons, but you can relate. From the Hounsfield units of the photons, you can convert this, if you have calibrated your CT, into the different range of the protons. And then you adapt the proton energy so that you compensate for any changes in the range, so you're sure to cover only the target volume. This is a whole field of medical physics, this treatment planning, how you do this correctly.
I see, really cool, thank you. And one more quick question. So you said that each patient needs the collimator to be designed based on the shape of their tumor, right? What is the material of the collimator and how large is it? Like, is it the eye socket size?
Yeah, let me bring the picture. We use copper because you need just material with a certain density to stop the protons. But copper, the isotopes that get produced during the irradiation, they are short-lived. So after 2 weeks, there's nothing that is radioactive anymore, and you can recycle the copper. And the size is more or less 1-to-1 the size of the tumor. So for the eyes, they are like this. But if you can do this kind of technique also for larger tumors, but then these collimators get large. And this means that the radiotherapy personnel, they have to manipulate these heavy collimators, and all the time they are touching material that is a little bit radioactive after the treatment. So these are all, this is another advantage why if you can do the magnetic scanning, you don't need this and you don't cause this kind of worries for the personnel. Yeah.
I see, thank you very much.
One more question over there. I don't know, because we have another discussion time after the
I
morning
have
session.
two short questions. about the beam scanning for transverse direction. This you use magnetic scanning.
Yes.
Okay. Do you suffer from hysteresis?
Yes. We have to take this into account.
Okay.
Yeah. We always go in a certain way.
So you cannot do it very fast, right? When you have to reverse the direction.
We take this into account.
Okay.
We take this into account. We do actually something which we call teaching.
Okay.
Before we treat the patient, we run, we measure the beam position, we see it's a little bit wrong because of the hysteresis, and then we overshoot so that we get the correct position. And then you can do it fast. You compensate for this effect. You have to do it always in the same way for one patient, but the plan does not change typically during the whole treatment of 6 weeks on the gantry. So what you have to do this teaching once, compensate for the hysteresis, and then you can use it and still be fast.
Okay. For deposit the beam into different depths, you use the beam.
The range shifter?
Yeah. So and that would suffer from the beam stacking, energy stacking.
Yes.
Yeah. And how much the depth that can. What is the maximum depth that you can use as techniques?
Yeah. So the range shifter which I described, this is gantry 1. This has 20 plates of 5 millimeter polyethylene, and it has about density 1, so 10 centimeters. So gantry 1 had used a few fixed beam energies and then do the fine modulation with this range shifter. Gantry 2, we can change the energy along the whole beam line. We move the degrader and we set all the magnets along the beam line according to the slightly changed energy, and we can do one energy step, which means 5 millimeter in the patient, in 80 milliseconds, which is very fast. And compensating the hysteresis along the beam line, you always come before you treat, you ramp the whole beam line to a maximum, you ramp the whole beam line to minimum, and then you go slowly up. So it's always in the same way.
Okay, thank
so
you.
we can do that with the beam line.
มีคำถามเป็นภาษาไทยไหมครับ โอเค In case some student or some people would like to
do I
ask.
have to do in Thai? No, sorry. I'm just have the question related to the FAT experiment, the FAT therapy. Yes, because you talk about the comparisons between electrons and proton. And my question is, how do they find this is FAT conditions? Because there are number that you say that, okay, this is conventional, this is FAT. And how do we know that this is already fresh, or it's that in between fresh and conventional?
Well, this is defined by the dose rate, and the dose rates, they were on the slides. It's a few centigrade, or it's a few hundred or thousand grade. This is the difference, flash and conventional.
Yes. And where are they come from? From the experiment results, or from some theory, something like that? Where are they come from, this number? Experiment based, I'm not sure.
Because
you know,
how we know the dose rate, you mean?
Yes, how do
We
you
measure,
know that it will have like fat conditions?
Yeah,
already?
we measure the dose rate. We have the dose monitors, and we know how much time we need to apply a certain dose, and this gives us the dose rate.
And you say that now you have fat condition because you do the experiment as well, right?
Mm-hmm.
So maybe I formulate my question a little bit. So this number come from the experiment. If you have the dose less higher than this number, and then you call this is fresh.
Yes.
Right.
Yeah.
So you see, you get a number when you do the experiment, and it shows the fresh.
Yes.
Results.
Yeah, we measure it. We measure it ourselves.
I see. Yeah. Okay.
And there now slowly publications are coming out. It seems a little bit that the flash effect is not so strong with protons, but maybe this is because protons are already very good.
Yes.
Maybe.
Yes.
But
maybe you don't need frat for proton, right? Okay. Thank you very much.
Okay. Yes. Because our next speaker is waiting. We will have more time afterwards.
Yeah.
It depends on the next speaker. Can you wait one more? Okay. One more question, please. There.
Thank you very much. I have a question about scattering and scanning systems. You said you change or you improve the speed of scanning magnets, and then you will compensate the moving of the organ. Is that right? And do you have a plan to replace, or to get into moving organ cancer using or utilizing scanning instead of scattering?
Yes, we not only have a plan, we are treating moving organs. We treat lung cancer, we treat other types of cancer using techniques of organ motion compensation that is possible with this fast scanning. It's now maybe not enough time to explain this, but one way is you give, say, 10% of the dose and repeat it 10 times. Then you get the same dose. But because you repeat it, the motion will wash out the dose inhomogeneities. This is one technique to do that. But
in the future,
it's a whole field. I cannot cover it in 1 minute.
then in the future, scattering system can be reduced utilization probably.
Yeah, we think that scanning has clearly advantages over scattering.
Because scattering lost a lot of beam, right?
Mm-hmm.
And you also have a beam spread of energy.
Exactly.
That's a problem.
Yeah.
So,
Exactly.
thank you very much.
Let's thank Martin again. So now we know that proton can be used for medical, but is it only outside Thailand? Can Thailand do this? Can our patient can be benefit from this technology? So let's hear from assistant professor, Thep, or medical doctor, right? I don't know how to say. Medical doctor Chakrapong Chakrabat from radiation oncologist, Chulalongkorn University Hospital or KCMH, King Chulalongkorn Memorial Hospital, Bangkok. Okay, so he will talk about proton therapy center at King Chulalongkorn Memorial Hospital, and with his direct experience to our patient from Thailand. Thank you.
Okay. Thank you very much, for having me here, and also thank you the organizing committee, to let me share, the experience of in Thailand, at King Chulalongkorn Memorial Hospital. First of all, I need to say, wow, for you, for PSI, that is the good thing, that I think we need to see in Thailand for the future. Martin already talk about the thing that happened in PSI, and that is many fancy things, and also many fancy things come through the practically things in the next year. That is the good thing. So first of all, I would like to share our experience of the treatment of the proton therapy in Thailand. And for me, my background is the medical doctor, oncologist, that take care of the cancer patient. So that's why most of all, I will talk about the clinical side, for the treatment of the patient. The good thing, Martin already talked about the difficult part for me. That is the physicist thing. Let me, this is the outline of my talk. First of all, I would like to talk about the introduction. just like a brief summary about the proton therapy and also the case and clinical application of the proton therapy, okay, that we use in Thailand. Okay, yeah, that is some history. Okay, yeah, you may all know that is the synchrotron already invented. Okay, since 1946 something. Okay, and okay, the concept of the proton treatment. Okay, yeah, built just like that time, and the first proton therapy treatment hospital bed machine. Okay, is at the Loma Linda University Hospital in USA since 1990. Okay, and this is the proton therapy that we have in Thailand. Okay, just like a pro beam system. Okay, that Martin already talked. Okay, the good thing. Okay, that we use the proton therapy as the treatment for the cancer is about the black peak. Okay, for okay, for the normal X-ray beam, okay, the beam profiles look like this. Okay, when we do the treatment, okay, there may be some just like a path through the skin, okay, and maximum dose, and then lower and pass through the body. Okay, but anyway, for the proton therapy, the good thing is about the black peak. That means the highest dose. Okay, we can identify and we can use the black peak. Okay, to highest dose at the tumor, while we can spare the normal tissue as much as we can. Okay, that is the concept of the treatment of the cancer. Okay, we maximize the dose of the radiation to the target. That means the tumor. And while if we can lowest the dose of the radiation dose to the surrounding normal organ, that should be the lowest complication that's going to happen for the patient. Okay, that is the concept of the treatment. And the proton therapy for the physical property. Okay, that is the good thing. Okay, that we can use for the treatment. Okay, this is the example of the plan. If we do the normal radiation, okay, just like this. Okay, the hot, okay, just like this at the area, like this, and the dose will drop and pass through. That means if there's some sensitive tissue, okay, around here, there may be some doses of radiation that tissue will receive. And for the proton therapy, the beam profile and the treatment paths look like this. We can specify the area and we can target the area, while we can spare the surrounding normal tissue like this. Okay, so this is the this is the cartoon, okay, of the comparison of the normal X-ray, okay, and also the proton. Okay, before for right now, okay, the conventional treatment, okay, that we use the many directions, okay, of the radiation of the photon, okay, to focus at the target spot. Okay, we can highest the dose at the tissue, okay, while just like a spread low dose, okay, to many for the surrounding organ. But for the proton, okay, we use the proton and the black peak, okay, let us spare, I think, almost all of the surrounding organ. Okay, that should be lowest the complication that's going to happen for the patient. Okay, Martin already talked about the concept of the intensity modulated proton therapy. Okay, that is the technique that we use in Chulalongkorn Hospital right now. This is the newer technique, okay, that we can do the pencil beam, okay, and do the radiation layer by layer, okay, and then the dose distribution, okay, should be really better to conventional radiation. Okay, so for the dose petting like this can improve the conformality to the target, while we can spare the normal tissue, surrounding tissue. This is the animation, okay, of the treatment, okay, that's going to happen for the patient. When the patient treatment, okay, patient need to stay still, okay, as much as they can, okay, and for the treatment, okay, we do the treatment layer by layer like this, okay, and to generate the dose to the target. Okay. That is the concept of the pencil beam scanning or intensity modulated proton therapy. Yeah, we do layer by layer like this, okay, so by control the beam, okay, by magnetic field. Okay, yeah, and this is also the just like an outline of our facility. Okay, we have the Synchrotron, we have the beam transporting system, and the big gantry. Okay, the table. Okay, that patient lie down just like this. Okay, that means for the treatment room, that just like this room. Okay, just only this area, but it for the big gym. Okay, for the treatment, for the Synchrotron, for the gantry, it's just behind the scene. Okay, for the patient. Okay, patient just see this area, and the controller for the doctor and for the technologies is just only this area. Okay, in Thailand, okay, yeah, we have the Proton Therapy Center. Our Proton Therapy Center is Her Royal Highness Princess Mahachakri Sirinthorn Proton Center. Okay, located at King Chulalongkorn Memorial Hospital. This is the first center of the Proton Center in Thailand and also in Southeast Asia. Now in Southeast Asia, we have I think the Proton Center is just open in Singapore. Okay, first treatment. Okay, we start the first treatment for the patient since August 2020. Okay, in our divisions, okay, we have the 3 CT simulation. Okay, that is the first process. Okay, for the treatment of the proton therapy. We have 2 MRI simulators. Okay, and we have 8 Linux machine right now for the treatment of conventional radiation therapy. Our proton machine, okay, is variant Pro Beam, okay, but we have just only 1 grantee. Okay, that means we need to quick set up the patient out of the room, okay, and then okay send the patient through if we have many patients. Okay, but right now the number of the patient is not much. Okay, that we can set the patient inside the treatment room. Okay, while we treat the patient. The technique that we use is the pencil beam scanning. Okay, and we can do the intensity modulated proton therapy. Okay, for I think the first step of the treatment before we need to do the patient, the volume, the treatment verification with the cone beam CT inside the treatment room. Okay, there are also the cone beam CT that we can compare the imaging. Okay, before the treatment and during the treatment and then set up the patient. Okay, to make sure we treat at the accurate site. And the table count, okay, in the treatment room is the 6D table count. Okay, that means when we have the imaging set, okay, before the treatment, and we have the cone beam imaging, okay, during the treatment, we can do the matching, okay, and the table count can adjust and in 6 dimensions. Right now we have about 25 to 30 patients per day. Okay, this is our journey. Okay, the project starts since 2014. Okay, we begin the project. Okay, and then okay the construction. Okay, just start from 2017. Okay, we start the construction. Okay, this is the Synchrotron. Okay, we install the Synchrotron. Okay, in 2019. And the first patient, okay, we start since 2021. Okay, yeah, there's a problem. Okay, during the COVID situation. Okay, that means when the Synchrotron, okay, and when the first patient is just like many just like 2 or 3 years, okay, because at that time there may be some problem of the installation, okay, because in Thailand, okay, we have no experience, okay, about the installation and calibration and setting up, okay, the proton machine, okay, that why it take time. And then, okay, we officially opening, okay, on 2022. Okay, this is our first patient. Okay, so until now, okay, I think we have more than 600 cases, okay, that we do the treatment for the patient so far. Okay, mostly, okay, just like liver cancer, CNS tumor, okay, some of the breast, okay, some of the lung cancer, okay, and I think the indication for the treatment, okay, we have just like a variety of the indication, okay, that I will talk after this. Okay, and as we talk, as Martin talked about the uncertainty, okay, that's going to happen. Okay, first of all, we need to make sure we hit the right position, we need hit the right target. So for the thing, okay, that is the key. Okay, for that, okay, I think it's from the simulation. We do the CT scan, we do the MRI to make sure, and the positioning is the key, okay, for the treatment as well, because if the air gap that happen or the just like a position, okay, that change, it just like it may affect to the beam that going to happen for the patient, and also for the treatment each day, okay, we need to do the image guided for verification. Sometimes we do daily. I think many cases, okay, such as this case, okay, when we do the planning and for the day of the treatment, if there's some different, if it match, okay, we need to do the replanning again, or the dose, okay, that we have before may not use for the patient. Okay, that's why that is the important, okay, that we have the cone beam CT inside the treatment room. Okay. And this is the dose planning, okay, that we can do in comparison for the patient. This is the case of the child patient, okay, that for some cases, okay, we need to do the treatment that we call the craniospinal radiation. We do the radiation through the brain and through the spine. If we do conventionally, okay, we can focus the radiation dose to the brain and to the spine, and there's many low dose of the radiation, okay, to the head and neck area, to the heart, to the lung, to the bowel, to the kidney, to the liver, something like that. That may cause the problem through the development of the child patient, of the children patient. The proton, okay, is really good in terms of dosimetric. Okay, we can focus the radiation to the target, okay, that we would like to treat. Okay, while we can spare, I think, many parts of the lung, of the heart, okay, for that patient. That should be better in the future for the children. The toxicity of the proton, okay, is the concern for the pediatric patient, of the children patient. That's why many cases, especially for the children, is almost always the indication for the proton therapy. And okay, this is some of the recommendation, okay, of the proton therapy treatment that may benefit for some kind of patient. Okay, that means I think we have the conventional machine, okay, that we use, okay, and we still use that, okay, and the proton, okay, should be good in many aspects, okay, but anyway, there may be some limitation of the resources, okay, that we cannot do the treatment of the proton for all patients, okay, so that's why many times, okay, we need to select the patient that may have the maximum benefit, okay, for the proton treatment, okay, so that is some kind of indication that we usually use the proton to the treatment. It's just like a pediatric patient, that means the children patient with the cancer, ocular tumor, okay, as Martin already told us, okay, the base of skull tumor, the spinal tumor, the malignant and benign brain tumor, the advanced unresectable head and neck cancer, paranasal sinuses, retroperitoneal sarcoma, hepatocellular carcinoma, that is the liver of the cancer of the liver, and the reirradiation. Okay, that is the indication. Okay, that proton may help us much in terms of some in terms of tumor control and some in reduce the toxicity that's going to happen. Okay, this is some of the case. Okay, for this case, okay, the patient has the mass here. Okay, this is the cross section of the body at the level of the base of skull. Okay, the white mass. Okay, this is the cancer. Okay, so for this kind of tumor, we need to treat with the high dose of the radiation. Okay, so for this area, is the area that the patient receives the doses of the 74 gray. For the surrounding tissue, like a brainstem and the spinal cord, okay, can tolerate the dose. It's just only for the brainstem, it's just like a 54 gray, while the spinal cord can tolerate the dose of the 45 gray, something like that. So for the conventional treatment, okay, we cannot escalate the dose of the radiation, okay, to as high like this. Okay, that means it may affect to the local control for this patient. For the proton, okay, especially for the skull base, okay, it can contribute the doses for the treatment of the patient like this, okay, which is good in terms of the reduce the complication, and can for the higher dose, okay, it can control the tumor much more better. And this also some cases, okay, that I would like to share. Okay, it's also the cancer of the base of skull as well. Okay, this tumor called the chordoma. Okay, for this patient, the patient received the operation and already did the conventional radiotherapy and then tumor recurrence. Okay, and after that, okay, they refer the case to us, okay, to do the further radiation that we call the reirradiation. For the first time, okay, that the patient did the radiation, okay, they did the highest dose as they can at that time. So that's why if we do the conventional radiation again, it can cause the significant toxicity for the patient. So that's why they send us, okay, for the proton treatment. Okay, this is the planning. Okay, for the planning process, okay, as Martin already explained, okay, we do the CT scan first, and we do the MRI. The CT scan, okay, we use for the planning, okay, because we need to have the half field units as the one of the factor for consideration for the dose, okay, and use the MRI as the imaging for target the lesion, and then, okay, we do the treatment planning. For the treatment planning, after that, okay, we have the dose like this. Okay, for this is the dose color wash. Okay, that means for this area, it's just like a dose of the radiation that the tumor received. Okay, and this is the follow-up. Okay, 1 year after proton radiation, we can reduce the size of the dose. Okay, while the patient can live, okay, with just like a minimal side effect. Okay, this is the thing that happened for the patient. Okay, and this also other cases. Okay, that I can share. Okay, this is a kind of the brain tumor. Okay, for this area is the area that the surgeon cannot do the operation, so we use the proton therapy in combination with the drug. Okay, with the chemotherapy that called the temozolomide, and this kind of patient do the further treatment with the target therapy that called the alpha-tinib. Okay, this is the follow-up imaging. Okay, sometimes we can use the radiation, the proton therapy as the combination of the treatment with the surgery. Sometimes we can use the proton therapy, okay, as the treatment for radiation, and we can also use the proton therapy in combination with the other treatment like a chemotherapy. Okay, and this is the example of the cases of the hepatocellular carcinoma in Thailand. Okay, we have the just like a pandemic area of the liver cancer, like hepatocellular carcinoma. Many times, okay, the patient, okay, especially for the cases that cannot do the surgical resection, okay, they send us to do the radiation. Okay, for this imaging, okay, is the conventional radiation. That means we spread the lower dose of the radiation, okay, throughout the body and focus as the area of the tumor. While if we do the proton, okay, we can spare many parts, especially for this part is the normal liver. Okay, that is the benefit of the proton. Okay, that we can use for the treatment of the liver cancer, because liver is the organ that really sensitive to the radiation. If we do the whole liver, if we irradiate the whole liver, okay, that may cause the toxicity that sometimes is irreversible and can cause the liver failure. Okay, and this is some cases, okay, that we use proton for the treatment. Okay, this patient is the breast cancer patient. Okay, for the conventional treatment, especially for the intensity modulated radiation therapy, that we use the proton, that we use the photon. Okay, the radiation. Okay, we focus this area. Okay, but anyway, for some area of the heart, okay, this is the heart, and some area of the lung, okay, receive the dose of the radiation. That sometimes it can cause the long-term complication, okay, especially for the heart. So when we use the proton, okay, the good thing, okay, we can spare, I think, almost all of the area of the heart, okay, for the lowest dose to the heart, okay, can lower chance of the complication that's going to happen in the future. This is also some cases of the esophageal cancer of esophagus. Okay, esophagus cancer is one of the challenging disease. Okay, because many times we do the focused radiation to the esophagus. Okay, and also the heart, the lung. Okay, that is surrounding organ. Okay, receive the dose of the radiation. Many times, okay, we cannot escalate the dose of the radiation as much as we can because of limitation of the lung dose and the heart dose that the patient cannot tolerate. So that's why when you use the proton, okay, the good thing, okay, we can spare many parts of the heart as well as the lung. Okay, and okay, I think almost all of my slide. Okay, this is the cancer of the prostate. Okay, prostate cancer is one of the good cancer. That means patient with the prostate cancer can live long. Okay, so that's why if we can find the effective treatment, okay, why we can save the side effect that's going to happen in the future. Okay, that should be the good things. Okay, so that's why when we use the proton therapy for the prostate cancer, the many part of the rectum, okay, here, and the bladder here is the surrounding organ. It can save or can minimize the side effect that going to be as the long-term side effect for that patient. Okay, so for the benefit of the proton therapy, I think the proton can reduce the radiation dose to the nearby normal tissue. Okay, and also can reduce the radiation-related adverse event. Sometimes, okay, radiation dose can escalate, okay, because of the proton therapy and the limitation of the normal tissue nearby, okay, can solved by the proton therapy. Proton therapy can also use as the real radiation for someone that did the radiation before and the tumor recurrence, and there may be some development of the new cancer at the area that we already did the treatment before. And for some patient with the higher risk of the secondary malignancy, like someone that have the genetic syndrome, like neurofibromatosis or some kinds of the genetic disorder, that even low dose operation can produce the secondary malignancy. The proton, the scatter dose that lowest to the surrounding normal organ, okay, can reduce the doses, reduce the risk of the secondary malignancy. But even proton has many benefits, but there may be some consideration point, that we need to concern, because first of all, the uncertainty, that happen, we see the black peak, if we have many techniques, the thing that happen is about the uncertainty. That means if we see the things, in the plan, but for the day as we do the treatment for the patient, there may be some different, because of the anatomy change, because of the position change, because of the technical things, So that is the thing that we need to take care, or we need to consider, because if sometime, there may be some lower dose to the target organ to us, or even higher dose, to normal organ, that can cause the significant problem to the patient. The second consideration, for the proton, we need more resources, for the treatment time, I think it's really much, compared with the conventional photon treatment, staff workload, because we need to have the staff involved in many steps, from the QA, from the planning, from the treatment, the staff workload, is the problem. So and the limited proton therapy center, in Thailand right now we have just only one center. I think in Thailand, next year, I don't know maybe how many years, we will have the second, we will have the third, we will have that, but anyway, right now we have just only one center, and we have just only single gantry machine, so that's why we need to find the priority criteria, and we need to create the good waiting list, for the patient. If we have the good treatment, but if it's not at the right time, it may not good, something like that. That is a problem. That is challenging, in our position in Thailand, and also the cost and the reimbursement policy. That is the key question, for us as well, because for the cost of the machine is quite high, cost of the maintenance, is also high. So that's why the cost of the treatment, is also quite high as well. So the reimbursement is the key of the problem. For some, right now the good thing, กรมบัญชีกลาง ครับ we can reimburse from the กรมบัญชีกลาง some of the government, can reimburse, with the indication, for something like this, but for someone, with the social security system, and the social welfare, cannot reimburse, that means they need to find the personal insurance for take care of that, or need to pay out of their pocket, for the payment. That means for the sometimes, that is difficult for me as the doctor. Sometimes we know the proton is the best way for that patient. But anyway, we cannot use that best treatment for that patient. That is the problem. So that's why we try to we try to do the project, okay, for the patient, especially for the children patient, okay, we try to do the fundraising, okay, for the patient that cannot do the proton therapy, just like cannot find the money, okay, to do the proton therapy, okay, and we hope, okay, especially for the children patient, okay, that they need to do the proton therapy, okay, there may be just like some chance, okay, to use that, okay, and ถ้าใครสนใจบริจาคก็ได้นะครับ ขอโฆษณา okay okay you can donate for this, okay, and it can also tax saving. Okay, for take-home message, okay, for the proton therapy can benefit for the cancer treatment. Okay, that is true. That is the fact. Okay, there may be some consideration point. Okay, need to be evaluated. Okay, before the treatment. Sometimes, okay, there may be some difference, just only some percent. Okay, between proton and the conventional photon. Okay, but for the cost, okay, there may be some big gap difference. It's just like maybe 10 times, something like that. Okay, so that's why this is the thing that we need to discuss with the patient, with the family, case by case. Okay, to consider proton, okay, as a treatment or just like the conventional treatment. Okay, that is the problem. But I think in the future, if the proton therapy is just like worldwide and the price of the new center, of the setup of the new center is cannot just like lower by the time. Okay, I hope the access to the treatment with the proton therapy much more easier. Okay, that is my hope in the future. Okay, and okay, we also have the website. Okay, if you would like to have some more information, or if you would like to have some question, or if we can do the collaboration in some aspect, okay, for some point, okay, I think please let us know. Okay, I think as me as the cancer doctor, oncologist doctor, okay, I don't say I ยินดีให้บริการ because I am the cancer doctor. Okay, but anyway, okay, if we have some collaboration, okay, for not the disease, okay, that is good. Okay, thank you very much.
Even though you would like to help us, but we don't want to be your patients. Hopefully, we will not see you, okay? Anyway, so more questions, please.
Thank you very much for very nice presentation. Yeah, Ajahn said that we still need maybe next year, the year after that, we still need more facility. So it means that many patients are investing list to be your patient, something like that. So in your opinion, if we want to have this facility because it's very expensive, so in your opinion as a medical doctor, so like maybe we should have in other area beside outside Bangkok, which place or any place of Thailand that you think we should have this facility? Yeah, thank you.
Yeah, really difficult question. Okay, but anyway, okay, if we look at the information, okay, of the radiotherapy machine, okay, the things, okay, that we already have right now, it's just like many radiotherapy machine is just located in Bangkok area. I think it's just like half of the radiotherapy machine is in Bangkok, but the other half, okay, is around the patient, around the country, something like that. Okay, so that's why for the distribution of the radiotherapy machine, it's not as good. Okay, now. Okay, but anyway, I think yeah, I think all of the region, okay, should have something like that. But anyway, that is the problem as well, okay, because for the how expensive of the machine, or just like for the workload or for the expertise, okay, there may be some problem as well, okay, to have many machine, okay, yeah, that is thing that I can answer right now. But if we observe, okay, the other country like Japan, okay, I think in Japan the treatment, the proton center is I think or region, okay, yeah, they have that machine, okay, that is a thing that we should follow. But anyway, the problem is the budget of the country and the reimbursement system. Yeah, that is the key. Yeah.
May I have additional question to this question? Just, we know that it's expensive, but could you please like how expensive?
Okay. As I told you, for the treatment, for each session, okay, it's around 40,000 baht for each session. Okay, that means for around 1,000 euro, something like that. Yeah, for one fraction. Yeah, just like that. Okay, if we do like for someone like 30 fraction, okay, it's around 1 million.
For 30 fraction, it should be 30,000 baht, right? For one case. ใช่ไหมคะ
ครับ
30,000 ต่อ 1 เคสใช่ไหมคะ
ประมาณ 40,000 ต่อ 1 เคสต่อ 1 fraction ครับ ครับ for one fraction ครับ
I have a question about the number of lung cancer patients, because it's the most frequent cancer evidence in Thailand. Is that right? If I'm right, I'm not quite sure. But the number undergoing proton therapy is only 6%, if I remember it right.
Yeah, that's right.
Why it's so low compared to the most
I think there may be many challenges for the treatment of the lung cancer. First of all, okay, for some cases, okay, that the patient can do the operation, okay, or the patient will send to the surgeon to do the operation treatment. And for the lung cancer, the problem, okay, is the cancer that mostly it can spread throughout the body, like can spread to the brain, to the bone, to the liver, something like that. Okay. For the proton therapy, just like for local treatment. Okay. For the state of the patient that disease spread, I think throughout the body. Okay. The radiotherapy is not, especially for the proton therapy, may not benefit much. Okay. So that's why that is a challenging. Okay. In terms of the patient that come to us. Mostly the patient come to us with the disease, with the state of the disease that spread, okay, throughout the body. That is the problem. And for some challenging is about the technical consideration, okay, because we do the proton and the lung is the one of the moving organ, moving target, okay. So there may be some challenging in terms of the treatment. We can use the technique for take care of that as well, okay, such as we do the radiation, we do the proton therapy in the position, okay, that the patient do the breath hold something, okay. But anyway, there may be more technique or more step, okay, that we need to do in the treatment. Yep.
So you may need the gantry the same as at PSI.
Yeah, we have that. Yeah. We have the gantry. Okay, but anyway, for the moving one. Okay.
Yeah, must be quick enough. I mean the speed, you can say, and then you can overcome the movement of the lungs.
Yeah. Sometimes we do that treatment we do that technique as well. Yeah.
So I have then the tumor that we can treat with proton therapy should be the well-defined border. Is that right? Not the higher grade, but the lower grade. Is that correct?
It's not right that it's just like if we can find the well-defined border, that should be good. But anyway, in terms of the treatment, we usually expand the margin of the treatment to the nearby surrounding organ to cover the microscopic extension. That may happen in mostly in the cancer. So that's why we can do the expansion for that. Yeah. Even operation. We need to do the thing like that as well. We need to cut the tumor plus the margin.
And then how about the tumor like glioblastoma, multiforme?
Yeah.
Could we treat it with proton therapy?
Normally, we usually not recommend. Not recommend. I cannot say like that. For the glioblastoma, it's not well-defined tumor. We need to expand. We need to expand the margin to cover the clinical target volume. To treat that kind of cancer. Anyway, for if we expand, the margin, the chance of the spare of the normal organ, sometimes it's not really easy. But anyway, for the glioblastoma, there may be some aspect, that we can use the proton therapy for the treatment. It's just like if we can escalate the dose of the radiation, that should be the better way in terms of for the treatment. There may be some clinical study that try to find the result of the treatment if we do the dose escalation to do higher dose than conventional radiation can, or even for the grade that lower, for some area, that involved with the neurocognitive things, such as the memory, such as the how fast of the thinking, something like that. If we can lower the dose to that area, we can save the neurocognitive things. That is the benefit of the proton therapy that may happen. For the treatment of the brain cancer, something like that.
ขอบคุณมากค่ะ
More questions? So I would like to, one.
Actually, I have one question. Like, does a patient receive the treatment planning and the treatment in the same day or different day? I mean, like, is it possible, like, the tumor getting bigger on the day that they do the treatments, like, compared to the treatment planning, like?
Yeah, that's right. Mostly, we do the treatment planning, and the treatment day, at different day, mostly around maybe 1 or 2 weeks, apart that, and there may be some change, but it's not much, something like that. And anyway, for the treatment, we do the cone beam CT inside the treatment room, but it is not good imaging, for evaluate the how big or how different of the size of the tumor, at the simulation day and the first treatment day. But anyway, there may be some chance of that. That means that is the problem to us for the treatment, especially for the proton as well, because sometimes we have the things, just like if for lung cancer, such as for lung cancer patient, in the treatment in the simulation day, just like only mass, there's no water, there's no fluid inside the lung, and for the first treatment day, it also has the fluid. That means it's may different the dose. That the patient will receive, something like that. Or for some technical thing like this. We need to do the re-simulation for the treatment. Okay, that is a problem. So that is one of the challenging things. Okay, because for the thing like this, okay, it may not change much. Okay, if we use the conventional photon treatment. Okay, but for the point like this, okay, is the thing that more important. Okay, when we use the proton treatment.
I see. So can I ask, like, how long you spend for treatment planning process? It's like for one case, how long have you done on one case, like for planning?
Mostly for
patients?
about 1 week.
1 week.
Yeah,
I see.
for me, okay, as the radiation oncologist, okay, I need to do the contouring, okay, of the tumor, of the target organ, okay. But good thing right now, okay, we have AI, some kind of AI to help us to contouring the normal organ, okay. But for target organ, I need to do myself, okay. For the planning, okay, if the case is really serious, okay, and we need to do it quite fast, okay. Many times, okay, it can for the planning, okay. Some dosimeters can do in just only 1 or 2 days, okay. Yeah, but mostly, okay. For the default, for the protocol of the treatment, okay. We need to have some just like 1 week, okay, for the planning. But for some case, if I ask, okay, and yeah, my kind colleagues, okay, can do it for me in just only some day. Okay, yes.
Thank you so much.
Okay. Another questions?
Okay, thank you for your presentation. Actually, I not understand most of your presentation because my background is accelerator physics. So I want to ask about your machine. In your presentation, the machine has already in service around more than 1 year, right? So is there any big problem with the machine or that you can share with us? Or if the machine have undergo big maintenance already, can you share with us?
Okay, in terms of that, okay, we have the service contract, okay, with the variants, okay, that we have to share the times, okay, for the maintenance, okay, such as, okay, we treat the patient from 8 a.m. in the morning until, yeah, we plan it just like until 10 p.m. something like that, and time after that is the time for the engineer, for the maintenance, something like that, and also for the big maintenance, okay, each year, okay, we have to have like we need to have like a 5 day around that, okay, to do the big maintenance, just like a yearly maintenance, something like that. That is the thing, and we also have the engineer, okay, that they stay at our center. I think, yeah, I think
engineer from Valiant, right?
Yeah, that's right. Okay, and I see the yeah, I think there will be some just like as I understand, as my understanding, okay, there's many sensor, okay, in the it's just like in the wall, okay, that just like I think maybe just like 100 sensors, something like that. And for the problem that happened, okay, is there's some problem, okay, there may be that sensor will alarm us, okay, and cause the interlock, okay, that happen. And okay, and when the interlock happen and the beam, okay, not come through, okay, as my wish, okay, the engineer need to find, okay, where is the problem as the source of the problem. Some can fix, okay, it's just only in some minutes, but some need to fix in just like some hours. And for the problem that need to find the part, okay, especially the part that may not in Thailand, may not be in Thailand, okay, there maybe need some days, okay, for the treatment, for that is a problem.
I would like just to comment on this reliability of the accelerator, because this is, and we have exactly the same one. So it's very reliable. In terms of service, we do 5 services of 3 days per year. And 3 days, it's weekend plus the Monday. So we don't need to really interrupt the patient treatments because they should not take long breaks. So, but 3 days is okay. And this is enough to do all the maintenance of the cyclotron and others. And in 20 years operation, 20 years, we had one major problem with the cryostat of the superconducting coil. and there we needed a shutdown of 1 month to repair that. But 1 month in 20 years is not bad. So it's really very reliable. Yeah.
Okay, any more questions? So if not, I just would like to ask, you have about 500 patients. How you justify, or how about the MST or median survival term, or any?
Yeah, I think that is the information, okay, that we plan to collect, okay, and we plan to report, okay, yeah, in the future, because as you may see, okay, for the more than 500 patients, okay, there's some difference of the indication of the cancer, okay, so and for just only 1 or 2 years, it's just like it's too short, okay, to evaluate the survival, okay, but anyway, in the future, okay, I think we will have the information, okay, to show, yeah, all of you.
But you said you could have 2 more machines in the future, so how can you justify that then? How can the government gonna give you that much money?
May not be, may not in Chulalongkorn, okay, we have run out of money right now. But anyway, okay, as my understanding, okay, there will be some center in Bangkok, okay, just like, yeah.
Or maybe in Chiang Mai, or maybe in Korat.
Yeah, I think maybe. Okay, but anyway, yeah, as okay, for like that, okay, I think, yeah, I think in Chulalongkorn, okay, we will be the pioneer, okay, for that.
Definitely,
okay,
yes.
And we will report, okay, the clinical information. As I told you, for in terms of the treatment, okay, that the survival, okay, and the just like overall survival, progression-free survival, okay, that is the end point, okay, that we need to evaluate, okay, at the same time, as I told you, for the proton, okay, the better thing, okay, that we can evaluate faster, okay, is the complication, okay, the things, okay, that I can share to you right now, okay, the complication that happened to the patient with the proton therapy is, I think it's better, okay, compared with the conventional one, okay, that we have.
Okay, thank you, the speaker. Let's give a big hand for him again.
Thank you very much.
And we would like to invite Dr. Dongmani, the acting director of the Thep Center, to give the souvenir for our speaker. So first, Dr. Martin, please. And then next, Assistant Professor, Medical Dr. Chakapong, please. Then we take a break for how many minutes? 5 minutes. Oh, no. Okay. Okay. All right. Okay, we come back 10:15, correct? 11. Oh, sorry, 11:15. Sorry, 11:15. So, thank you. Martin showed us that at PSI, the proton accelerator is a playground for some physicists. So now I would like to say the same thing. The proton therapy machine at KCMH is also the playground for Thai physicists as well. And you will understand more when Dr. Narongrit from Suranari University of Technology tell us what did he do. He has to go to KCMH at night and do something, and in the morning he has to remove the thing, and the doctor use it to treat the patients. Okay, you hear it, please. Thank you.
Thank you. You steal my joke now. Okay. Okay, I'm Naronglit Litjoho. I'm from School of Physics, Institute of Science, Suranari University of Technology, SUT. And today I'm gonna talk about a project that we are trying to develop in SUT and also the Proton Center at KCMH in the topic of the development of the proton computer tomography or the PCT prototype. Well, in this project, we are not only work in this SUT and KCMH, but we also have some collaboration from Bergen University of Norway and also CERN. Well, first of all, I will tell you what is the PCT. PCT is another type of medical imaging instead of X-ray CT. There are some benefit of the PCT over the X-ray CT scan. Well, as you have already learned from Martin and also Dr. Chakapong in the first two talks, this is the proton therapy. I mean, then today I think you heard about from the developer of the accelerator and doctor, and then today I talk about the user. I mean, okay, based on my experience, my father has cancer, also brain cancer. I just want to say that in the beginning, how you know that you have cancer? My father start from, he cannot say the thing correctly. He called remote control as a sister. He called sister as a remote control. He cannot count the number correctly, and then he kind of missed memory. And then we sent him to the hospital. The doctor do CT scan, that is X-ray CT scan, and immediately found 2 tumors in his head. And then immediately the doctor said, okay, we have to do a brain operation. I don't know, for me, he just need to open the scalp and then take the tumor out and then close it. He took like several months to be recovered. Because at that time, that is 8 years ago, at that time we have no proton therapy. And after that, there also some, it was found that the brain tumor that come from lung cancer. And then he still have to do chemotherapy and then the radiotherapy because it was spread out already. And then also some spot inside his head also. And then I think, okay, this is the disadvantage of the operation and also chemotherapy and also radiotherapy, right? Well, then the proton therapy take an advantage because you no need to open your scalp, you know? I mean, then you just shoot a proton inside the patient head and then, okay, let proton deposit energy here. And then another advantage is that the proton deliver lower dose to a normal tissue and higher dose to directly to the tumor tissue. And then now, luckily, it is available at KCMH now. Well, there are also some disadvantage of the proton therapy because it has a high operating cost. You need an accelerator, you need technicians around to run the accelerator, and then you need a large space for the facilities compared to the radiotherapy or chemotherapy. Well, but what is the problems here? As you can see from the picture of Dr. Chakapong in this morning, when the doctor prepared to do the proton therapy, they has to do the treatment plan. What is treatment plan is he has to draw a picture of the proton, that which direction the proton shouldn't go, how many doses that the proton have to deposit here. But the image that come from the diagnostic part is the image from X-ray CT, right? I mean, let's imagine that what is X-ray CT? X-ray CT is the black-white gradient picture, right, or 3D modeling. This means that picture tell you how much your organs or your tissue absorb the X-ray, but not how much the proton will deposit inside that tissue, right? But won't it be better if we can construct a picture or an image of a particle body with the proton that tell that which kind of organ, how many dose of the proton will deposit the energy into that organ directly, and that will be better. And for sure, there are already some calculation, a lot of publication review that, okay, PCT or the proton CT scan would be slightly better stopping power compared to the normal CT. This means X-ray CT is not really 100% compatible with the proton therapy. If you have the proton CT, is more compatible with more compatible with the proton therapy with lower the uncertainty in this case. This is the first reason of good things of the proton CT scan. The second thing is, when you do the X-ray CT, the doctor cannot repeat the X-ray CT that often, because the patient will accumulate higher dose, right, more than limit. This means the doctor have to wait for a while and then do again the CT scan. And we expect that the proton CT would deliver a lower dose compared to the X-ray CT, because the proton CT, you just shoot the proton throughout your body and then didn't have a black peak in your body for the proton CT. And then compared to the X-ray CT, it can be lower dose compared to the X-ray CT, and this means that we can do more often proton CT compared to the X-ray CT, and that would be good for the treatment for the doctor. And the last thing is, another thing is sometimes, I don't know, I'm not sure, X-ray CT, you need the contrast media, no? You have to inject the contrast media to do this, and then it's not good for your kidneys, but the proton CT is not really require this. The next thing is, for the X-ray CT, for the, when the doctor asks you to do the X-ray CT, then you have to do it today, and then for the next week or someday you will do the proton therapy. This means there are some times in between, right? But if you have the proton CT, you can just do it 5 minutes before the treatment. I mean, maybe exaggerate, but okay, won't it be better if because we use the same machine, right? We use the proton beam. This means it's also possible that we can have an integrated system. You imagine your patient body just, I don't know, some minute, some hour just before the proton therapy start, right? This would be good. I mean, at least there is no less chance that tumors or cells that move or the patient body change, location of the cancer change, I don't know, but okay. Then the three main important thing is, first is the proton CT should give a slightly better the proton stopping power map for the proton therapy. Second is maybe the patient accumulate lower dose, and the last one is you can have an integrated system for the proton therapy. Well, and I summarize into this picture. You can see, proton therapy is better in the stopping power, lower dose accumulation, don't require the contrast media, integrated system. But the disadvantage of the proton CT is that the scanning time. Nowadays, when you go to the X-ray CT, you just move the X-ray source, no, in the circle. But it will faster than you have to move the gantry. Right, then proton CT should give a higher scanning time. And the next thing is the operating cost. You pay more when you move a gantry compared to moving the X-ray source. Right. Well, then come to what should proton CT look like? What is the component of the proton CT? First thing, what you need is, of course, the proton beam, where we luckily have at KCMH. The next thing is, you probably need a tracker. We should track the incoming proton coming out, and then a phantom as the representative of the patient, and then another tracker to track the particle, the proton, after scattering from the phantom. The next thing is you need calorimeter to measure the residual energy of the proton after passing through this, and then the DAQ system. And this is our latest prototype of the PCT that we are currently developing. You can see that, okay, we have a proton, actually, okay, I didn't move the gantry here. I mean, gantry should be here, and then proton come from the right to the left, and then here is the acrylic we are going to use as the phantom. It is a 1/4 of the cylinder acrylic, and then these are our range sampling calorimeter that I will talk about this later. And you can see this part is the motion part, which I can be able to move the phantom in 3 dimensions, and also rotating stage here. We can do like 3 dimension plus rotation part automatically. Well, to access the proton therapy, actually this project is not started by me, but Ajahn Chinorat start. And then to access the proton therapy in 2017, V means SUT, CMU, SLRI, and KCMH signs MOU with the GSI, and then we are able to access the proton center at KCMH, and also biological laboratory at CU, at Chulalongkorn University also. And well, from the customer part, the Proton Center in Thailand, it starts from 2020, actually 21. The first, it's delay actually, it probably should be 2020, but okay, 1 year delay, I think. And then the energy of the proton is 70 to 220 MeV. Actually, this energy is slightly lower than the proton CT, because if you want to shoot proton from one side of your body to another side, you need around 250 or more MeV. But okay, we have to do what we have. Then I think maybe hand CT scan or head or some small animals, we can probably do the proton CT in the near future. And then a pencil beam with 5 to 7 millimeter, 1 sigma Gaussian beam. It depends on the energy. When the energy is low, 70 MeV, the beam is bigger, 7 millimeter. And when the energy is high, 220 is 5 millimeter. And we are able to operate in 2 modes, that is Partian mode and QA mode, which are able to access some signal. And moreover, we also signed the non-disclosure agreement with the variants, where we have to get, where we are able to get to know some electronic parts of the variants when we would like to get a signal of the proton beam. Well, let's go to the principle of the PCT. How can we get an image from this? Well, first, if a proton comes to a matter, what you have is the inelastic scattering, multiple Coulomb scattering from the nuclei. And then with this, what happens is proton will lose energy inside this sample, and will also deflect from the original direction. This means you have the proton come and then deflect and then deposit some energy. What we have to do here is we're gonna have to track the proton before and after passing through a phantom, and also measure the energy that after passing through the phantom also. Well, because the multiple Coulomb scattering, the principle to do the image reconstruction is not like X-ray, right? X-ray, you just export the X-ray, and then let's see that how much you have in the X-ray left. You have a black-white picture because some organ absorb the X-ray. But here you have to get an information from the energy that really deposit, which should be related to the electron density of the phantom of the organs. And also for the spatial, you probably need to know the angle that really the proton really deflect. But of course, due to the multiple Coulomb scattering, you probably need a clever algorithm to track the proton that really see what is the dimension, or you probably need a higher statistic to really track the proton. Then, as I told here, the requirement is more than 250, more than 220 that we already have. One, probably think about the booster of the proton center at KCMH that we also trying to think, but also, of course not easy. To boost the energy higher than 220, and then we are able to penetrate the adult trunk, and then okay, and then here is some better Bosch formula, and then finally, if you know the energy in and energy out, and then we are able to get the E here, I think we'll get the electron density from this image. We hope we can do image reconstruction. Now the question is, how can we track the particle? How can we measure the energy? Then thanks to another collaboration with CERN, Ajahn Chinorat also have collaboration with CERN. He part of the ALICE experiment with, in the past we are developing the innermost tracking system we call the ITS, or innermost tracking system part. This part of the detector consists of an array of a sensor. This sensor named Alpine sensor. It is a large ion collider. Sorry, that is ALICE. The Alpine sensor is the silicon-based monolithic active pixel sensor, which is the part of the ITS here. I should go to this. It is the CMOS sensor, which we are able to measure any charged particle that coming through here. And it has a very, very powerful sensor because it has low power consumption. Low budget material means the sensor is very thin, only 50 microns. And also it has very high resolution. You can see the size of the sensor here is only, for example, this sample is 3 centimeter times 1.5 centimeter. And then there is 1024 times 512 pixels here. The pixel size is 28 times 28 micron. Well, with this, it also have high efficiency, 99%, and then a small fake hit, this one. Well, this sensor was think to be a prototype, part of the prototype of the PCT to track a particle. But the small sensor have to be put in an array to become a larger sensor. This idea was developed by the back-end PCT development teams, where we also collaborating with. This is the model, and this is the one that they are developing. This guy is the Professor Dieter from University of Bergen, and this is me. And then we visit them. But luckily, the sensor is we still don't have a sensor, because the sensor is super difficult to produce, and it was produced in Ukraine. And then there's some trouble with the sensor that we are not really able to get the sensor, you know. I mean, it's only once in the world that the sensor was characterized, was produced. This means this group, the backend group, also was delayed. Their project was delayed also. Yeah. Okay, but we also discussed with them, and then we're trying to test a smaller prototype to use a smaller sensor. Here is this is the sensor area that become our calorimeter, where we're gonna put 2 of the Alpine sensor in this area. But again, luckily we don't have a sensor. Then this model we have, and then we buy everything except sensor. And then we are not finishing yet the sensor. And then I come back and think again what we can do with our existing sensor in our laboratory. We have only one Alpine sensor here. And then we think like, okay, we think another way. Instead of we shooting proton beam, I mean, here they're gonna shoot like, can be a cone beam. And then you can shoot 1 times and then get it to do image reconstruction. But because we have only very small sensor, what I can do is I fix the small sensor, I fix the proton beam, and then I scan the object instead. Then we are able to use a small sensor to scan the big object. This is our idea to use what we have. Okay, we are poor. Then the first thing that we have to do is, okay, get the signal from the proton to open our sensor. Because to shoot the proton beam to a sensor, it have to be a good timing. I mean, I have to open or trigger the sensor at the same time the proton coming in. This means I have to get the signal from the proton center as KCMH and read out the signal, and then produce another signal and put into the sensor to open the sensor. And it was successful test by a single shift test. With this, we also playing by putting a pen in front of the sensor, putting a copper plate on top of the rotational state. We can able to verify that, okay, everything is synchronized. I open the beam, I rotate the sample, I detect the proton at the end. But of course, I don't have a good picture of the pen because it's scattering. And then we come to more complicated part. We put the 3 sensor in an array and put the proton from the top to the bottom. And then here we want to verify a tracker, the one part of the PCT. And then the proton coming in, shooting through this sensor, and then we get the information. This go inside a dark box to reduce the noise. And then we go back to more complicated one. We have 6 sensor. This is our last 6 sensor. I cannot break any one of this. And then, okay, we shoot the proton through. But here we also would like to test the calorimeter. How to have a calorimeter? The idea is the sampling calorimeter where we put the absorber material in front of the sensor here. Then this means that the proton deposits some energy inside the absorber, and then the number of proton reduced with the multi-layer of the sensor should tell you the energy of the remaining proton. But luckily we only have 6 layers here. I mean in the models of the backend they have like 41 layers of the sensor. But here we would like to proof of principle that what we have here. And then we shoot the proton passing through here. Well, the calorimeter can be another things. We also think about something else apart from the sensor. Then we think about the glass scintillator calorimeter. Some of our students do the glass, produce the glass at the glass lab in Nakhon Pathom, Rajapat Nakhon Pathom University. With this glass, there are some combination of the material science that when the proton hit, it should emit light, let's say. Then we really produce the glass ourselves, put inside this box. There is some light collimator, and then there is a light detection, and then we really found the light that coming out from this glass after we shooting proton in. This means we really can produce the glass scintillator ourselves here. And then I put in the water to be a phantom, and then we move the location of the glass here. Well, this one I told you this is the calorimeter. We have to put the sensor and then the absorber in the layers, or we can put all of them be a glass scintillator or any kind of scintillator. Well, come to our related parts. Because we have to move, then we have to do something automatically. I mean, we have to really put the wire inside the wall of the partition room and control room to control the proton beam from the control room, to move the phantom from the control room, to open the beam from the control room. And then I have a quick video, I think. Not available, so sad. Okay, actually I told you this is our 6th sensor that we have. The proton should come from this direction, and the phantom is here, and then our sixth sensor is here. Then to control everything synchronizingly, this is the hard things that we also produce. We call it the trickle controller system. The trickle controller system control the proton beam through the TSS box of the proton therapy. This means we are able to control the proton on and off in our desired parameter that we input. Actually, this one take an advantage of. At KCMH, there is a trigger additional system to measure the height of the body for the movement cancer. If you're breathing in and then the height of your body is higher, then it stop shooting proton, and then it lower it. They can again shoot a proton again. We took an advantage of this one and produced our own electronic device that can really turn on and turn off the proton beam in our desired time. And then this guy also connect to the rotational state and three-dimensional state motion, and also go to our sensor. And here we also test that, okay, we open the proton beam first, open the outpie, and then after that we are able to rotate the things in. Then another I would say another problem is because the proton that coming in, there are too many protons. Because if I remember correctly, it's 10 to the 9 proton per second or something. Maybe I'm wrong, but it's too many proton come to our sensor. This means we have to produce the collimator. We just make a collimator from the acrylic and then reduce the number of proton that we are able to measure the proton beam. But without the collimator, we have the beam look like this in our sensor. Then to do a track reconstruction, to get an image, we have to do a track reconstruction. We do a simulation from Jan 4 simulation, and then this is a 70 MeV, a bit spread beam, and then this is higher energy. And then we get the point from the simulation in order to track. And then one of our students calculate do a track reconstruction and calculate the efficiency of the track reconstruction. And then here, with the higher energy, you can track better than lower energy because this is more widespread. And then this is our result. Actually, this is super preliminary result. I mean, we have the beam of the proton that passing through the collimator. We have a 6 point here from the sensor that we have. He produced the algorithm to track the proton. And here is the proton that he can really track without any phantom, without any absorber. And this project is still going on and not finished yet. I would say this is kind of a progress of this project. We hopefully now I would say we are able to develop the hardware in our desired level. I mean, we are happy with our hardware already. Now turn into the software part. We have to really do develop the software, develop the algorithm to track the proton, and then use this information of the proton and also the proton energy to become the image reconstruction in the future. And I think this is all of my talk today. We love take picture. This is my team. Thanks. Thank you.
Sorry that I steal your joke. But anyway, so one thing that I would like to say that even though we're lacking of the resources, but this makes us try harder. And short of the money, but we are not short of the ideas. Okay, question please.
Very nice work, thanks a lot. You showed the outline of the detector and you have the trackers in front and on the back, but can we see the trackers on these photos?
Which photo? Sorry. You
Show-
mean
show
you mean the
the,
first one, no? The
Show the schema of the, this was this one.
This one, okay.
Yeah, you have this brown tracking chambers
Mhm.
in front of the phantom and downstream of the phantom. And can I see the trackers on this photo?
No. We don't have only 6 sensors. I mean, okay, if I take this one, if I take the, I mean, we use the same sensor, we have only 6 sensors. We don't have, we use the same sensor to test the tracker, right? I just test the tracker that we are really able to track the proton. And then I take the same sensor and turn it into the calorimeter and then test the calorimeter. Then I would say this one don't have the tracker yet because our limitation of the sensor.
Okay, thanks.
Yeah.
So my question just relate to the resolutions that you expect to get from your system compared to the one at backend or compared to the CT scan.
Well, to be honest, we are not reached that state, but we just follow some publication. There are many publications talk about the image reconstruction of the proton CT, or most, I would say, I could say most of them saying that the resolution is better than the mono CT. Actually, this graph show the dual energy CT, X-ray CT scan, and single energy CT scan. You can see the uncertainty. Actually, the relative residual error on the y-axis is higher than the proton CT. There's some calculation that okay, the uncertainty is lower than the X-ray CT. But we are not reached that state yet.
Okay.
Our postdoc doing that now.
May I have another question? So you said that now you use like only a single sensor, or maybe just only a few sensors. Do you have plan that maybe in the future, if you have more money and you can get more sensor, to have a kind of array sensor, to have faster scan?
I think Ajahn have a plan.
So we collaborate with Alice and we learn some sensor technology from CERN. At the end, if we have enough support and enough people, we would like to develop this sensor here in Thailand. And we have one PhD from Indonesia, Abdul. He will, can you show you? Get up, yes. He will be one of the main guy of our SUT that finally, it doesn't matter who said, CERN got this, PSI got that, and the question is, what Thailand has? So if we have enough support, I have to say that the software to design the sensor, it costs about 8,000 baht per year. Okay, it's not cheap. And once you get the sensor design, you have to send it to the foundry, and to get one bunch, you have to do 3 to 5 million baht per bunch. This one doesn't count about the wafer and circuit, everything. So at the end, if you want to do something, I would have said that if you want to do deep technology or high technology, you need high investment and high talent, okay? Not just your dream, no? We want to do digital 4.0, but we have 0.1 budget. Okay, sorry about that.
But it's true. Thank you.
Yeah, but we have to prove to them that we can do something first, because before we can ask for more budget. Okay? Sorry. Thank you.
I have a question about the range of protons. Because now you have a phantom of how many centimeter thickness?
This one is 5 centimeter only.
So how about if we want to, what is the target organ that you will have a proton?
We just use acrylic now. This is the easiest one that we can produce. Then,
but I mean, if you want to do for the real organ, the range of 250 MeV protons is only 38 centimeter. Then it will stop inside the phantom, actually.
You did.
So we can't do PT tomography by this energy. Do we have any plan, or do we have any suggestion on this? Because otherwise the proton will stop already. We can't detect any proton that transmitted to the detector.
So this part I have to answer then. I'm sorry. Anyway, I have to stay in your scene, no? You don't? So actually, what we try to do first now, we have another team called Radiobiology team, led by Dr. Dayar, which is postdoc of mine, and another postgraduate researcher, Prawa. We have to do the, we call in vitro experiment. We want to try to do the cancer cell line. We culture it, and we put it on the well plate. We want to try to first try to see that our proton can distinguish between cancer cell and normal cell or not by using the standard phantom. You mean the CAP-FAN one or whatever. That's our plan, because the well plate is not so thick. The well plate, the phantom for the biological sample. So that's the first way that we want to do it. And after that, we plan to do the in vivo animal model, like mouse that Martin showed. But this one, I will lock it, okay? I don't let them run around. And finally, as you mentioned, and I also would like to sell more research at SUT, is that we also aim at GBM, glioblastoma, multiforme, whatever, or recurrent one. This one is not so thick compared to the torso body. And at SUT, in about 6 to 10 years from now, we also going to do another technology we call the BNCT, boron neutron capture therapy, which is a binary radiation system. So I would have said that from now on to the 10 years, Thailand will be in the exciting time of the particle therapy. We will have proton, we will have neutron, and of course at Chiang Mai, Professor Sakon also mentioned about flash, and we would like to do that. We have dream, but we have to go there.
So I mean, in the real life, we have the body which is thicker than 38 centimeter. What is the solution? That's the question.
Actually, this one, if you have 250 MeV, it can penetrate your trunk.
Yeah.
Then you have to boost the proton. Actually, one have to think, I don't know, I think PSI also have this project before. I think they have the project to have the booster, no? Booster that higher energy than 220 MeV. At that case, you can have enough energy.
We did proton radiography, so it's not a CT, but just like a normal X-ray. And at that time, we did not have our superconducting cyclotron, but we were using parasitically the 590 MeV cyclotron of PSI. And that allowed us to shoot through the, well, not patient, but we did some animal images with that. But that's long ago. This was in 95. And then we decided not to follow up on this. But it's of course a very valid approach, and you measure directly the proton range. So this is why this is so interesting.
So in short, you do two things. First, increase the energy of proton, and the second one, just take the organ out. Just like you did for the patient eyes. You just cut it open and take it out.
So you need the bigger synchrotron and then. But another question concerning about proton, which produce neutrons as well. Do you have to take it to account for neutron production when you shoot proton into the body?
Actually, yes, because in our calorimeter consists of the absorber. There are many candidates of the absorber, for example, copper, aluminum foil, aluminum, or carbon fiber. We have to think about which one that produce the secondary radiation less. Yeah. Now we didn't care about the radiation yet because we have very few materials. We do check with the survey meter, but it's there for us for sure. But in the future, yes, of course, we have to think about that.
Okay, sorry, I have to cut it short now because the next speaker is waiting. I'm sorry. That takes too much time. Thank you, Dr. Naronglit. Okay, the next speaker, could you prepare for your slide? And I would like to introduce Miss Moli Pan Dang Prasert. She will explain about how to use synchrotron to produce some what we call radiopharmacy. She's, I think, director of radioisotope at TINT, Thailand Institute of Nuclear Technology. Okay, thank you.
Thank you very much. สวัสดีค่ะ My name is Molipan. My name is Molipan Dang Prasert from Thailand Institute of Nuclear Technology, and my background is pharmacist. So today my topic is about the production of radiopharmaceuticals. Since at the beginning, I have been informed that I may present in Thai. So this is, I think, we are running out of time, and to make it quick, and I apologize that I would be better for me to present in Thai. Okay, but for those who are not Thai, you can follow my slides because they are all in English as well. So, switch ไม่ทัน ก็จะก่อนที่จะเริ่มการผลิตสารเภสัชรังสีเนี่ยนะคะก็อยากจะขอเคลียร์นิดนึงว่าสารเภสัชรังสีเนี่ยมีที่ใช้ในโรงพยาบาลตรงไหนบ้างนะคะในโรงพยาบาลเนี่ยจะมีหน่วยที่เป็นเกี่ยวกับรังสี3หน่วยคือรังสีวินิจฉัยรังสีรักษาแล้วก็เวชศาสตร์นิวเคลียร์หลายๆท่านเนี่ยจะสับสนว่าสารเภสัชรังสีเนี่ยเป็นรังสีรักษาหรือเปล่านะคะมันไม่ใช่นะคะก็ถ้าเป็นรังสีวินิจฉัยกับรังสีรักษาเนี่ยจะเป็นการใช้รังสีจากเครื่องนะคะในขณะที่เวชศาสตร์นิวเคลียร์เนี่ยเป็นการใช้ยาก็เป็นradiopharmaceuticals นะคะรังสีวินิจฉัยกับรังสีรักษาเนี่ยเครื่องกำเนิดรังสีเนี่ยจะอยู่ภายนอกร่างกายแต่ว่าของนิวเคลียร์เมดก็จะเป็นเอารังสีเข้าไปอยู่ภายในร่างกายนะคะแล้วก็ให้มันแผ่รังสีออกมาข้างนอกนะคะก็จะใช้ได้ทั้งวินิจฉัยแล้วก็รักษาส่วนประกอบของเรดิโอฟาร์มเนี่ย2ส่วนใหญ่ๆก็จะเป็นเรดิโอนิวคลายกับยานะคะที่ทำหน้าที่เป็นแคริเออร์พาเรดิโอนิวคลายนั้นไปที่ target organ นะคะหลังจากที่เราผลิตโทษค่ะหลังจากที่เราผลิตเรดิโอฟาร์มโดยการเอาเรดิโอนิวคลายเนี่ยเลเบลเข้ากับสารนะคะไม่ว่าจะเป็นสารเคมีเป็นลิแกนเป็นเพปไทด์โมโนโคลอนัลแอนติบอดีหรือว่าสารชีวโมเลกุลใดๆก็ตามนะคะแล้วก็ได้เป็นเรดิโอฟาร์มาซูติคอลขึ้นมาเนี่ยหลังจากฉีดเข้าไปให้คนไข้แล้วเนี่ยนะคะมันก็จะไปที่อวัยวะเป้าหมายนะคะมันใช้ได้ทั้งสำหรับการรักษาแล้วก็การวินิจฉัยถ้าวินิจฉัยเนี่ยเราก็ต้องใช้เรดิโอนิวคลายที่ให้รังสีแกมมาหรือโพซิตรอนนะคะถ้าให้รังสีแกมมาเนี่ยเราก็จะไปสร้างอิมเมจด้วยสเปกนะคะหรือสเปกซีทีแล้วก็ถ้าเป็นโพซิตรอนเนี่ยก็จะสร้างภาพด้วยเพชรนะคะถ้าเป็นการรักษาเนี่ยก็จะเป็นตัวที่ให้เบต้าหรือ อัลฟานะคะอันนี้เป็นตัวอย่างของ radionuclides ที่ใช้ในเวชศาสตร์นิวเคลียร์นะคะสำหรับการรักษาพวกสเปก radionuclide เนี่ยตัวเด่นๆที่สุดที่ใช้มากที่สุดก็คือเทคนีเซียม 99M แต่ถ้าเป็นพวกเพชร radionuclide ตัวที่ใช้มากที่สุดก็จะเป็น F18 นะคะซึ่งวันนี้เนี่ยเราก็จะลงไปที่ F18 เยอะหน่อยเพราะว่าเป็นตัวที่ผลิตจากไซโครตรอนนะคะส่วนทางด้าน treatment ตัวหลักๆที่ใช้มากที่สุดก็คือไอโอดีน131นะคะตัวต้นใหม่ที่ตอนนี้เริ่มใช้มากขึ้นก็คือลูทีเซียม177แล้วก็มีพวกอัลฟาอิมิเตอร์เพิ่มเข้ามานะคะทีนี้สเต็ปของการผลิตยานะคะradiopharmaceuticals เนี่ยเราก็จะเริ่มจากการผลิต radioisotope ก่อนซึ่งradioisotope ทางการแพทย์เนี่ยเราจะมาจาก2แหล่ง2วิธีใหญ่ๆก็คือผลิตด้วยเครื่อง reactor กับผลิตจากไซโครตรอนนะคะหลังจากที่เราได้สารไอโซโทปรังสีแล้วเนี่ยเราก็เอามาผลิตต่อเป็น radiopharmaceuticals โดยการเอาไปเลเบลกับสารต่างๆนะคะที่มันเฉพาะเจาะจงกับแต่ละโรคแต่ละอวัยวะนะคะจากนั้นผลิตได้ยาแล้วเนี่ยก็ต้องมีการ QC ก่อนที่จะส่งให้คนไข้สำหรับ reactor produced radionuclide ก็คือจะเป็นพวกนี้นะคะอันนี้เป็นตัวอย่างของradionuclide ที่ผลิตจากไซโครตรอนจะสังเกตนิดนึงว่าถ้าผลิตจาก reactor เนี่ยสารตั้งต้นธาตุตั้งต้นกับธาตุที่ได้จากการบำบัดด้วยนิวตรอนเนี่ยจะเป็นธาตุเดียวกันนะคะในขณะที่ของไซโครตรอนเนี่ยจะเป็นคนละธาตุนะคะอันนี้ก็บำบัดด้วยนิวตรอนใน reactor นะคะอันนี้ reactor ก็ข้ามไปเลยแล้วกันพารามิเตอร์ที่สำคัญในการผลิตนะคะอันนี้สำหรับ reactor นี่ก็คือเป็นจะขึ้นอยู่กับจำนวนของสารตั้งต้นที่เราใช้นะคะค่า cross section ของปฏิกิริยาที่จะเกิดขึ้นนะคะแล้วก็นิวตรอน flux เวลาที่ใช้ในการ irradiate รวมถึง half life ของตัวที่เราต้องการผลิตด้วยเพราะระหว่างที่เราผลิตไปมันก็สลายไปด้วยไปเรื่อยๆด้วยนะคะทีนี้พอมาถึงเรื่องของไซโครตรอนนะคะหลักการนี้เราคงข้ามไปเลยนะคะเพราะฟังมาตั้งแต่เช้าแล้วนะคะปฏิกิริยาของเรทของการเกิดนะคะของการเกิด radionuclide เนี่ยก็จะคล้ายๆกับตัว reactor นะคะเพียงแต่ว่าเปลี่ยนจากนิวตรอน flux เป็น beam current นะคะทีนี้ฟังก์ชันที่สำคัญของการผลิตโดยไซโครตรอนเนี่ยก็จะเป็นเรื่องของพลังงานของ particle ที่เข้าบำบัดนะคะก็ส่วนใหญ่แล้วradionuclide ทางการแพทย์ที่ใช้ผลิตจากไซโครตรอนเนี่ยก็จะใช้บำบัดด้วยโปรตอนนะคะซึ่งพลังงานของโปรตอนที่ใช้บำบัดเนี่ยก็จะมีความสัมพันธ์กับค่า cross section ของปฏิกิริยาดังนั้นเนี่ยเวลาที่เราเลือกใช้พลังงานที่จะผลิตแต่ละตัวเนี่ยเราก็ต้องมาดูที่ตรงนี้นะคะอย่างเช่นสมมติว่าเราจะขอโทษค่ะสมมติว่าเราจะผลิต F18 นะคะ F18 ค่า cross section เนี่ยจะสูงสุดอยู่ที่พลังงานประมาณต่ำกว่า10นะคะเพราะฉะนั้นไซโครตรอนที่มีพลังงาน10 MeV เนี่ยก็จะสามารถผลิตได้ในขณะที่ถ้าเป็นแกลเลียม67นะคะช่วงพลังงานที่จะให้ค่า cross section สูงสุดเนี่ยก็จะอยู่ที่ประมาณเกือบ30 MeV นะคะเพราะฉะนั้นเนี่ยmedical proton medical cyclotron ที่ปกติใช้กันเนี่ยก็อยู่ที่ประมาณ20 MeV เนี่ยก็จะไม่สามารถผลิตแกลเลียม67ได้นะคะทีนี้นี่ที่ส่วนโปรตอนเมื่อเราเร่งอนุภาคแล้วเนี่ยมันก็จะชนกับ target นะคะตัว target คือสารตั้งต้นของเราเนี่ยก็จะอยู่ใน target station ซึ่ง target station เนี่ยก็จะมีอยู่3รูปแบบด้วยกันขึ้นอยู่กับสถานะของสารตั้งต้นที่เราจะใช้นะคะก็จะมีทั้งที่เป็น solid target liquid target แล้วก็ gas target นะคะตัวที่เป็น liquid target นี่ก็คือว่าสารตั้งต้นเราเนี่ยเราจะเคลือบไปบนbacking material อันหนึ่งนะคะซึ่งเพลททำการเพลตติ้งโค้ดให้มันเป็นผิวบางๆอยู่บน material นี้นะคะแล้วก็เอาไป irradiate นะคะการโคตติ้งเนี่ยก็จะใช้ไฟฟ้าในการโค้ดนะคะเป็น electroplating ถ้าสารตั้งต้นเราเป็นของเหลวนะคะหรือเป็นแก๊สก็จะเป็นแชมเบอร์ที่เป็นตัวเป็น target station นะคะพอirradiate เข้าไปแล้วก็จะส่ง target ที่ irradiate แล้วเนี่ยไปที่ hot cell เพื่อทำการ purify เพื่อให้ได้ไอ radioisotope ที่ต้องการนะคะสำหรับตัวหลักของเราจากไซโครตรอนเนี่ยก็คือ F18 นะคะที่ใช้กันมากประมาณ 90% เลยนะคะ F18 เนี่ยก็จะผลิตจาก O18 นะคะที่เป็น enriched water เป็นน้ำนะคะก็จะใช้ liquid target อันนี้นะคะหลายๆตัวเนี่ยก็สามารถผลิตได้จาก target หลายชนิดนะคะอย่างเช่นแกลเลียม68เนี่ยจะสามารถผลิตได้จากเป็น liquid target ก็ได้เป็น solid target ก็ได้นะคะก็ต้องไปดูที่ผลการทดลองของแต่ละตัวว่าตัวไหนแบบสภาวะไหนจะได้ยิวที่ดีกว่ากันได้ purity ดีกว่ากันนะคะสำหรับ F18 นะคะสารตั้งต้นของ F18 ที่บอกแล้วว่าเป็น enriched water เป็น O18 นะคะซึ่ง parameter ที่สำคัญเนี่ยก็คือ enrichment ของสารตั้งต้นอันนี้นะคะต้องมากกว่า 95% เนื่องจากว่าถ้ามันน้อยกว่านี้เนี่ยมันก็จะมี O16 ปนอยู่ด้วยนะคะ O16 ก็จะทำให้เกิดimpurity N13 ขึ้นมานะคะนอกนั้นตรงนี้ก็คือเป็นcondition ของการผลิตทั่วๆไปนะคะก็จะใช้เวลาประมาณ2ชั่วโมงทีนี้ข้อดีของการผลิตของ radioisotope ที่ผลิตจากไซโครตรอนอย่างที่เมื่อกี้นี้ได้บอกแล้วว่าถ้าเราผลิตจาก reactor เนี่ยธาตุที่ได้กับธาตุตั้งต้นเนี่ยมันจะเป็นธาตุเดียวกันเพราะฉะนั้นการทำ chemical separation เนี่ยจะค่อนข้างยากมากนะคะการที่เราได้ธาตุคนละชนิดกันเนี่ยทำให้เราสามารถpurify ออกมาได้ดีกว่านะคะแล้วก็ specific activity ก็จะสูงกว่าแล้วก็ในสมัยนี้เนี่ยการเข้าถึงไซโครตรอนเนี่ยก็จะง่ายกว่าการเข้าถึง reactor นะคะทีนี้หลังจากที่เราได้เรโดนิวคลายมาแล้วไม่ว่าจะจาก reactor หรือจากไซโครตรอนก็ตามนะคะเราก็จะต้องเอามาผลิตเอามาเลเบลต่อนะคะเพื่อที่จะได้เป็นยาที่เฉพาะแต่ละโรคแต่ละอวัยวะนะคะบางตัวเนี่ยเมื่อ purify บางตัวเมื่อ purify ออกมาจากไซโครตรอนได้เป็นเรโดนิวคลายแล้วเนี่ยบางตัวมันก็สามารถใช้เป็นยาได้เลยนะคะแต่ทั้งนี้ทั้งนั้นพวกนี้เป็นยาฉีดก่อนที่จะไปใช้กับคนไข้ก็ต้องผ่านการ sterilize ก่อนนะคะทำให้ปราศจากเชื้อและไพโรเจนนะคะส่วนไอโซโทปอื่นๆนะคะก็จะต้องมีการไปเลเบลกับยาตัวอื่นเพื่อให้เป็น specific สำหรับแต่ละโรคนะคะสำหรับเมืองไทยจริงๆแล้วก็คือที่มีใช้ก็คือพวกนี้นะคะแล้วก็แกลเลียมโดตาเทตแกลเลียม PSMA นะคะอันนี้ด้วยค่ะ 41 พิปนะคะสำหรับอัลไซเมอร์ค่ะที่บอกว่าพระเอกของไซโครตรอนเนี่ยมันก็จะเป็น FDG นะคะ FDG เนี่ยก็จะเป็น fluorodeoxyglucose ที่เลเบลด้วย F18 นะคะทีนี้เรโดนิวคลายที่ผลิตได้เนี่ยจะแบ่งออกเป็น2ประเภทใหญ่ๆคือประเภทที่เป็นเมทัลเป็นโลหะนะคะกับพวกที่เป็นนอนเมทัลอย่างฟลูออรีนเนี่ยจะเป็นพวกที่เป็นนอนเมทัลเวลาที่เราเอาไปผลิตต่อเป็นสารเภสัชรังสีเนี่ยมันก็จะเป็นพวกออร์แกนิกซินเทซิสนะคะก็จะปฏิกิริยาก็จะค่อนข้างยุ่งยากนิดนึงก็เพราะฉะนั้นเนี่ยปฏิกิริยาพวกนี้เนี่ยเราก็จะผลิตอยู่ในใช้ซินธิไซเซอร์นะคะซินธิไซเซอร์เนี่ยก็จะอยู่ในฮอตเซลนะคะหลังจากที่เราได้irradiate ออกซิเจน18มาแล้วเนี่ยตัว irradiate target ก็จะถูกส่งมาที่ hot cell นะคะแล้วก็ purify ออกมาเป็น F18 แล้วก็เข้า synthesizer เพื่อทำปฏิกิริยาพวกนี้ออกมาเป็น FDG นะคะอันนี้ก็เป็นตัวอย่าง F โดปาอีกตัวหนึ่งสำหรับพาร์กินสันนะคะ F โดปาก็จะเป็นโดปามีนอะนาล็อกนะคะทีนี้สำหรับเรโดนิวคลายที่เป็นโลหะก็จะง่ายกว่านั้นมันไม่ต้องเข้าเป็นขบวนการ organic synthesis นะคะก็จะเป็นการform complex กับตัวลิแกนนะคะซึ่งอย่างเช่นแกลเลียมเนี่ยก็จะ form complex กับตัวลิแกนตัวนี้ซึ่งตัวลิแกนตัวนี้เนี่ยก็จะเอาไปเชื่อมต่อกับ เปปไทด์กับโมโนคลอเรนแอนติบอดีกับแมคโครโมเลกุลอะไรก็ตามที่จะสเปซิฟิกต่อมะเร็งแต่ละชนิดนะคะแต่ทีนี้โมเลกุลพวกนี้กับพวกลิแกนตรงนี้เนี่ยมันจะเป็นโมเลกุลค่อนข้างใหญ่เพราะฉะนั้นการที่จะเอามาอยู่ใกล้ๆกันเนี่ยมันก็อาจจะมี Select Effect นะคะก็เลยจะต้องมีสเปเซอร์มีลิงเกอร์ตรงนี้เชื่อมด้วยนะคะทีนี้ที่บอกว่าจะง่ายกว่าพวก FDG ตรงนั้นก็เพราะว่าจริงๆแล้วในคอมเมอร์เชียลอะค่ะมันมีโมเลกุลนี้ทั้งโมเลกุลขายเลยนะคะเราก็ซื้อทั้งโมเลกุลนี้มาเลยแล้วก็เลเบลเข้ากับแกลเลียมเข้าไปนะคะขั้นตอนก็จะง่ายนะคะอันนี้ก็อาจจะไม่มีซินเทไซเซอร์ใช้ได้ไม่มีซินเทไซเซอร์แล้วก็สามารถใช้แมนนวลในลามินาร์โฟลว์ได้นะคะหลังจากผลิต radiopharmaceuticals ได้แล้วเนี่ยก็ต้องเป็นการ quality control นะคะเริ่มจากที่เราต้องดูว่า radionuclide ไอเดนก่อนว่ามันใช่ตัวที่เราต้องการไหม purity ได้ตามลิมิตไหมนะคะยาหลายๆตัวจะมีเป็นโมโนกราฟอยู่ในฟาร์มาโคเปียก็จะยึดตามลิมิตตามนั้นนะคะอย่าง radionuclide identification กับ purity เนี่ยเราก็จะใช้ gamma spectro นะคะดู radiochemical purity ก็คือว่า radionuclide ที่เราต้องการนั้นน่ะมันอยู่ใน chemical form ที่เราต้องการหรือเปล่านะคะอย่างเช่นว่าถ้าเป็น FDG ก็คือ F18 จะต้องอยู่ในฟอร์มของ FDG ทั้งหมดไม่มี free F18 เหลืออยู่นะคะradiochemical purity เนี่ยส่วนใหญ่ก็จะใช้วิธีทางโครมาโตแกรมนะคะแล้วก็ใช้วัดด้วย radiochromatograph scanner นะคะ chemical purity radiodissolved solvent ก็คือปกติแล้วเวลาการ synthesis เนี่ยบางวิธีก็ต้องใช้ organic solvent ซึ่งจะต้องกำจัดออกให้หมดนะคะตรงนี้ก็จะใช้เป็น HPLC กับ GC ในการวิเคราะห์นะคะแล้วก็อย่างที่บอกว่ามันเป็นยาฉีดเพราะฉะนั้นก็ต้องมี sterility กับ endotoxin ด้วยนะคะหลังจาก QC หมดแล้วเนี่ยถึงจะ release ยาแล้วปล่อยไปให้ผู้ป่วยได้นะคะอันนี้เป็นตัวอย่างของ radio farm ทั้งหมดไม่ทั้งหมดนะคะเป็นตัวอย่างของ radio farm ที่มีในเมืองไทยนะคะตัวสีแดงก็คือตัวที่ผลิตด้วยไซโครตรอนนะคะทีนี้ FDG ที่บอกว่าใช้กันมากนะคะก็คือใช้สำหรับเป็นการวินิจฉัยมะเร็งนะคะโดยทั่วไปเลยเนื่องจากว่ามะเร็งเนี่ยมันจะเป็นเซลล์มะเร็งเป็นเซลล์ที่เจริญเติบโตผิดปกตินะคะก็จะต้องมีการใช้กลูโคสมากผิดปกติด้วยเพราะฉะนั้นเนี่ยมันจะเป็น high uptake ของกลูโคสตัว FDG เป็นกลูโคส analog เพราะฉะนั้นมันก็จะเข้าไป uptake ได้สูงในเนื้อเยื่อที่เป็นแคนเซอร์ด้วยนะคะก็นอกจากจะใช้ในการไดแอกแล้วเนี่ยก็ใช้ในการทำสเตจจิ้งของระยะโรคนะคะการติดตามการรักษาแล้วก็ดู recurrence ของตัวมะเร็งนะคะอันนี้ให้ดูเป็นไลฟ์ไซเคิลของ FDG เลยนะคะเริ่มตั้งแต่ O18 enriched water เข้าไปในไซโครตรอนradiate ตรงนี้นะคะประมาณ2ชั่วโมงได้เป็น F18 ออกมานะคะเข้าซินเทไซเซอร์ผลิตออกมาจะเป็น FDG ตรงนี้ก็อีกประมาณ30นาทีนะคะพอมาแล้วก็มาถึง QC นี้ก็ต้องทำทั้งหมดนี้ให้เสร็จภายใน1ชั่วโมงหรือ1ชั่วโมงครึ่งนะคะถึงจะรีลีสยาออกมาแล้วก็ฉีดให้คนไข้ได้นะคะเพราะฉะนั้นสเต็ปตรงนี้ทั้งหมดน่ะก็จะประมาณไม่ต่ำกว่า4ชั่วโมงเพราะฉะนั้นในไซโครตรอนเซ็นเตอร์ทั้งหลายที่มีอยู่เนี่ยเขาก็จะเริ่มผลิตยากันตั้งแต่ตี2นะคะทุกที่ทั่วโลกค่ะอันนี้ทั่วโลกค่ะก็จะเริ่มกันตั้งแต่ตี2แล้วก็พอแบบ6 โมงเช้า7 โมงเช้าอย่างเงี้ยก็จะเริ่มรีลีสแล้วก็ส่งยาไปที่อื่นได้นะคะทีนี้พอฉีดยาให้คนไข้แล้วเนี่ยโดสของคนไข้ปกติยาทุกตัวนะคะจริงๆแล้วเวลาคำนวณโดสคนไข้เนี่ยจะคำนวณต่อกิโลกรัมนะคะก็ทีนี้คนไข้ที่แต่ปกติก็จะอยู่ประมาณ 5-10 มิลลิคูรีนะคะของ FDG พอฉีดเข้าไปแล้วเนี่ยก็ต้องให้คนไข้นั่งรออยู่ประมาณ1ชั่วโมงเพื่อให้ clearance ออกจากระบบเลือดนะคะเพื่อลดแบ็กกราวด์เวลาที่ไปสแกนเนี่ยแบ็กกราวด์จะได้ไม่สูงนะคะจากนั้นก็เข้าเครื่อง PET CT สแกนนะคะตรงนี้ก็แล้วแต่ performance ของเครื่องค่ะใครมีเครื่องดีก็15นาทีเสร็จ ค่ะหรืออีกถ้าเครื่องธรรมดาก็30นาทีนะคะจากนั้นภาพที่ได้ออกมาเนี่ยก็จะเป็นแบบนี้ภาพแรกจะเป็นภาพของเพชรนะคะภาพตรงกลางเป็นของ CT และภาพนี้เป็นภาพที่ฟิวส์รวมกันระหว่างเพชรกับ CT อันนี้เป็นไซโครตรอนในไทยนะคะที่มีอยู่น้องใหม่ล่าสุดก็คือมอ.สงขลาทีนี้อย่างที่บอกว่า access to Synchrotron เนี่ยมันง่ายกว่า reactor เพราะฉะนั้นเนี่ยงานวิจัยของไอโซโทปรังสีใหม่ๆเนี่ยจะมีค่อนข้างเยอะนะคะก็อันนี้เป็นตัวอย่างของที่มีงานวิจัยในที่เขาทำกันค่ะก็จะเป็นนิมิตหมายที่ดีที่เราจะมีไอโซโทปตัวอื่นไม่ต้องพึ่งพา reactor มากนักค่ะก็สุดท้ายสทน.เองยังไม่มีไซโครตรอนนะคะยังไม่ได้เริ่มเปิดเดินเครื่องยังไม่สำเร็จก็ตอนนี้ก็คือยาที่เรามีให้บริการอยู่ก็คือประมาณแค่นี้ค่ะก็ขอบคุณค่ะ
Questions, please.
ขอบคุณมากครับปกติเวลาที่เราสังเคราะห์ออกมาเราก็จะคำนวณยิวใช่ไหมครับไม่แน่ใจว่าอย่างอันนี้คือเราจะคำนวณยิวยังไงเพราะว่ามันก็น่าจะขึ้นกับเวลาด้วยเพราะมันสลายตัวไปด้วยเพราะมันจะส่งผลต่อการคำนวณโดสที่จะฉีดให้คนไข้ต่อไปด้วยใช่ไหมครับ
ไม่ค่ะโดสเราคำนวณตามน้ำหนักอยู่แล้ว medically ใช่ไหมพอเราผลิตออกมา
แต่เราก็ต้องรู้ยิวตอนว่าเราสังเคราะห์ออกมา
เราวัด activity ได้นะคะยิวออกมาว่าสังเคราะห์แล้วเสร็จแล้วกระบวนการทั้งหมดเสร็จแล้วได้ยามาเท่าไหร่กี่ medically ค่ะแล้วก็ dispense โดสให้คนไข้ตามนั้นเลย
โอเคครับก็คือต้องคำนวณยิวทุกครั้งหลังจากที่เรา
วัดค่ะวัดทุกครั้งใช่ค่ะปกติถ้าเป็น FDG เนี่ยได้ประมาณ 50% ค่ะ
More questions? Or you are hungry already? Okay.
ขอถามหน่อยนะคะก็คือถ้าเป็นแบบนี้ก็คือจริงๆของสทน.เองไม่ได้รักษาอยู่แล้วเนาะเพราะฉะนั้นถ้ามีลูกค้ามาซื้ออะไรอย่างเงี้ยค่ะในการจัดส่งหรือช่วงเวลาหรือระยะทางที่ต้องพิจารณาในการจัดจำหน่ายหรือมีลูกค้ามารับซื้อนี่เขาจัดการยังไงคะ
เราก็จะทำเฉพาะตัวที่มี half life ยาวสามารถจัดส่งได้ค่ะส่วน F18 เนี่ย110 นาทีถ้าเรามีไซโครตรอนแล้วเนี่ยก็คาดว่าเรายังส่งได้ค่ะ
แล้วบริเวณล่ะคะเพราะว่าอย่างที่เชียงใหม่เนาะเคยไปคุยกับเขาก็บอกว่าในภาคเหนือเนี่ยก็คือพอได้แต่เขาไม่มีเพชรไม่มี CT อะไรอย่างเงี้ยค่ะเพราะฉะนั้นก็ทำเองใช้เองที่เชียงใหม่อะไรอย่างเงี้ยแต่อย่างของสทน.เนี่ยค่ะก็คือ area ที่ให้บริการได้อะค่ะครอบคลุมถึงประมาณไหนบ้างคะ
ได้นะคะเพราะจากที่รู้ว่าขอนแก่นเขาก็สั่งจากจุฬาภรณ์ค่ะ4 ชั่วโมงไปได้ค่ะก็พรีแคลไป
4 ชั่วโมงใช่ไหมคะขอบคุณค่ะ
Okay, so if there is no further questions, so maybe we can discuss over lunch. And I would like to invite Dr. Domani to give the souvenir to our speakers. First, Dr. Nalonglit, please. And then Kun Bolipan, please. Okay, thank you. So I think that concludes the morning session, and in the afternoon we still have more talks, so please stay with us. Thank you.
ก็ก่อนที่เราจะไปรับประทานอาหารกันนะคะเราทางผู้จัดมีของที่ระลึกให้ท่านอาจารย์ชินรัตน์นะคะที่กรุณามาเป็นแชร์เซสชันแล้วก็เป็นผู้นำอภิปรายให้เราด้วยนะคะขอเชิญอาจารย์ดวงมณีและก็อาจารย์ชินรัตน์ค่ะ ขอบคุณอาจารย์ชินรัตน์มากนะคะขอบคุณค่ะ